October 12th, 2019. While you were sleeping, something passed through our cosmic neighbourhood. Not a satellite, not space debris, not even a comet born in our solar system. This visitor came from somewhere else, entirely a place so distant that light from its home star might never reach Earth in your lifetime. Its name 3I/Atlas, the third interstellar object ever detected. But here's what keeps astronomers awake at night. It wasn't dead. It was active, spewing gas and dust as it hurtled past the sun at speeds that would make our fastest spacecraft look like they're standing still. You see, we've spotted interstellar visitors before. Oumuamua, that mysterious cigar-shaped rock. Borisov, the rogue comet. But 3I/Atlas, it's different. And when scientists started crunching the numbers, when they began to understand what this object truly represents, they realized something absolutely terrifying. This isn't a rare event. This is the norm right now. As you watch this, countless objects from alien star systems are silently drifting through the darkness between planets. Most of them we'll never see coming. If this cosmic mystery grabs you like it grabs me, show some love with a like and subscribe when you're genuinely hooked. Of course. Now, let's dive into what makes 3I/Atlas the visitor that changed everything. September 10th, 2019. Gennady Borisov, a Ukrainian amateur astronomer, was doing what he'd done hundreds of nights before, scanning the sky from his homemade observatory in Crimea. His 0.65-metre telescope wasn't fancy. No $1 million grant funded it. Just a man, his passion, and the darkness above. And on that night, he spotted something moving. Something that didn't belong. Fast forward 1 month, October 12th, 2019. The Atlas survey system in Hawaii, an automated network designed to catch asteroids that might threaten Earth, flagged another anomaly. Moving fast, moving wrong, the computers calculated its trajectory, ran the numbers twice, then 3 times, and that's when the alerts started flooding astronomical networks worldwide. Because this wasn't just another space rock. You need to understand something about our solar system. It's not a snow globe. It's not sealed off from the rest of the galaxy. But for most of human history, we assumed it was. We watched comets appear, tracked asteroids, mapped every piece of debris we could find, and all of it, every single object, was ours. Born in our cosmic backyard 4.6 billion years ago, trapped by the sun's gravity, endlessly circling like goldfish in a bowl, until 2017. That's when Oumuamua showed up. Strange name. Right, it's Hawaiian for scout or messenger from afar arriving first. And boy, did it live up to that name. Oumuamua came screaming through our solar system at 196,000 miles per hour on a trajectory that mathematically proved it came from somewhere else. Another star system. Another origin story. We spotted it on its way out already leaving. Like a guest we didn't even know had attended the party. Scientists went absolutely wild. Telescopes around the world swiveled to track it, but Oumuamua was already fading, tumbling through space, refusing to give up its secrets. Was it a comet, an asteroid? Some researchers, and I'm not making this up, even suggested it might be an alien probe. Harvard astronomer Avi Loeb published papers arguing it could be artificial. Why? Because Oumuamua accelerated as it left the solar system, like something was pushing it. No visible gas jets, no obvious explanation. The scientific community mostly rolled their eyes at the alien hypothesis. But here's what nobody disputed. We just confirmed that interstellar objects do visit our solar system. The question wasn't if anymore. It was how often 2 years later. Gennady Borisov answered that question. his discovery officially designated 2I/Borisov was different from Oumuamua in one crucial way we caught it early. While it was still approaching the sun, while there was time to study it, and this one looked like a comet. It had a tail. It was outgassing. It behaved exactly like the comets born in our own Kuiper belt, except for one tiny detail: it came from another star system. Imagine that. A comet that formed around an alien sun, got kicked out into interstellar space, wandered the galaxy for millions or billions of years, and then, purely by chance, happened to pass through our neighbourhood. Dr. Piotr Guzik from Jagiellonian University in Poland, who studied Borisov extensively, put it this way: this is the first time we've been able to study an object from another stellar system in the same detail we study objects from our own solar system. The data that came back was mind-blowing. Borisov's gas composition looked similar to comets from our solar system, but not identical. Its carbon monoxide levels were higher, much higher, suggesting it formed in a colder environment than anything in our cosmic backyard. Scientists estimated it might have originated from a red dwarf star system, where temperatures are frigid and ice dominates the landscape. But here's where your brain should start tingling with unease. If we found 2 interstellar objects in 2 years, how many did we miss? Think about it. Oumuamua was only discovered because it passed relatively close to Earth, about 15 million miles, which in space terms is basically brushing shoulders in a crowded subway. If it had been just a bit farther away, or if it had come from a slightly different angle, we would never have known it existed. Borisov, same story. Gennady happened to be looking at exactly the right patch of sky at exactly the right time. In 2019, Dr. Gregory Laughlin from Yale University ran the calculations. His team estimated that at any given moment there are roughly 10,000 interstellar objects within Neptune's orbit, 10,000 just passing through, most of them small, dark, invisible to our current technology, like trying to spot a handful of gravel thrown across a football field at night while wearing a blindfold. And then came number 3. 3I/Atlas arrived with less fanfare than its predecessors. No dramatic headlines, no alien speculation. The astronomical community was almost getting used to these visitors by now. But as observatories turned their instruments toward this new object, something strange emerged in the data. It was active, releasing gas, creating a thin coma, that fuzzy cloud of vapour that makes comets look like they're glowing. But here's the weird part. 3I/Atlas was really far from the sun when it started doing this. About 600 million miles away, roughly Jupiter's distance. Most comets don't wake up until they get much closer, heated by solar radiation. But 3I/Atlas was already outgassing, already active, like it brought its own heat source from wherever it came from. Dr. Kwanzi Yi from the University of Maryland, who led some of the initial observations, noted that 3I/Atlas showed unusual activity for such a distant object. The spectrum of its coma revealed water vapour, but also hints of other compounds, carbon dioxide. Maybe cyanide compounds materials that sublimate at different temperatures than regular water ice. What does that tell us? That this object, this visitor from beyond, formed under conditions we're still trying to understand? Maybe it came from a star system with a different chemical makeup than ours. Maybe it experienced events during its formation that we've never witnessed. Every interstellar object is like receiving a postcard from an alien world, except the postcard is written in a language we're just beginning to learn. But let's zoom out for a second. Let's talk about what you're probably feeling right now. Maybe a little uneasy. Good. You should be, because 3I/Atlas, Borisov and Oumuamua aren't the anomalies. We are. We're the ones living on a tiny wet rock, assuming our solar system is some kind of protected sanctuary, while the rest of the galaxy plays a never-ending game of cosmic billiards. Think of it this way: you live in a house. You've always lived in that house. You know every room, every creaky floorboard, every scratch on the wall. And then one day you notice muddy footprints in your kitchen. Someone walked through. Someone you never saw, never heard. They didn't knock. They didn't ask permission. They just passed through while you were sleeping. And now you realise the door was never locked. It was never even closed. People, things have probably been walking through your house for years, and you just never noticed. That's 3i/Atlas. That's what it represents, Doctor. Matthew Holman from Harvard Smithsonian Center for Astrophysics said in a 2021 interview, "These interstellar objects are forcing us to reconsider how we think about the solar system. It's not a closed system, it's more like a busy highway, and we've only just started counting the cars. And the traffic is about to get a lot heavier, because in 2025 the Vera Rubin Observatory in Chile will come fully online. This beast of a telescope will scan the entire visible sky every few nights, detecting objects 100 times fainter than what we can spot now. Astronomers estimate it'll find dozens, maybe hundreds of interstellar visitors every single year. What took us from 2017 to 2019 will soon happen monthly. Are you ready for that? Ready to know just how many uninvited guests are cruising through our cosmic living room, but knowing they exist is only the first step. The real question, the one that should keep you up at night, is what happens when we actually understand where these objects came from, what forces ejected them into the void, and what their presence tells us about the violent, chaotic, utterly terrifying nature of the galaxy we live in. Because here's the thing about 3i/Atlas that nobody wants to say out loud, calculating its trajectory backward. Tracing its path through space is like reading a crime scene in reverse. And what that math reveals isn't just interesting, it's disturbing. The math doesn't lie, and when it comes to 3i/Atlas, the math is absolutely screaming at us. Let me walk you through what happened in those first weeks after discovery. Astronomers around the world started feeding positional data into orbital calculation software programs with names like OrbFit and Find_Orb that sound boring but are basically cosmic detective tools. They plot where an object was, where it is, and most importantly, where it came from. For anything born in our solar system, the numbers always work out neat and tidy. You get an ellipse, a closed loop around the sun. Maybe it's a tight circle like Earth's orbit, or maybe it's a stretched out oval like Halley's comet, but it's always closed, always coming back. The math gives you what's called an eccentricity value between 0 and 1. 0 is a perfect circle. 1 is the most stretched ellipse possible while still being bound to the sun. 3i/Atlas. Its eccentricity came back at 1.999. That number should make you uncomfortable. Anything above 1 means the orbit isn't an ellipse, it's a hyperbola, an open curve, the mathematical signature of something that came from beyond and will return to beyond. 3i/Atlas isn't circling back for a reunion tour. It's gone. One and done. But here's where it gets truly wild. That trajectory allows us to rewind time. We can calculate exactly where 3i/Atlas was 1 million years ago, 10 million years ago. We can trace its path backward through the galaxy like running a movie in reverse. Doctor. Yee's team at the University of Maryland did exactly that. They published their findings in early 2020 and the results were, well, let's just say they raised more questions than answers. Rewinding 3i/Atlas's trajectory for approximately 4 million years, accounting for the sun's motion through the galaxy, the gravitational influences of nearby stars, the whole cosmic dance they tried to pinpoint its origin. It didn't come from any star system we can definitively identify. Let that sink in. This object travelled for millions of years through interstellar space. During that journey, you You personally went from not existing at all to watching videos about space on a device that would have seemed like magic to your great-great-grandparents. Entire species evolved and went extinct on Earth. Our ancestors climbed down from trees, invented fire, built civilizations, and landed on the moon. And all that time, 3I/Atlas was silently drifting through the void, crossing distances so vast that light itself takes years to traverse them. The velocity is what really messes with your head. When 3I/Atlas entered our solar system, it was moving at approximately 34 kilometers per second relative to the Sun. That's about 76,000 miles per hour. Sounds fast. Right. Let me put it in perspective. The Parker Solar Probe, humanity's fastest spacecraft ever built, reached a top speed of 430,000 miles per hour during its closest approach to the Sun. That's our best achievement. Decades of engineering, billions of dollars, cutting-edge technology. And 3I/Atlas, this random chunk of ice and rock, was cruising at a respectable fraction of that speed with no propulsion system. Just raw momentum from whatever event kicked it into interstellar space millions of years ago. Think about the violence required for that. To accelerate a comet, something that could be anywhere from hundreds of meters to kilometers across to those speeds, you need energy on a scale that makes nuclear weapons look like birthday candles. We're talking planetary collisions, close encounters with massive gas giants, maybe even gravitational slingshots around stellar remnants. Dr. Amaya Morrow-Martin, an astrophysicist who specializes in debris disk dynamics, explained it this way in her 2019 paper. Every interstellar object is evidence of catastrophic dynamical events in its birth system. These are not gentle departures. Something violent happened. So what violent event created 3I/Atlas? The most likely scenario: a young planetary system, chaos incarnate. You see, when star systems first form, they're not the orderly, clock-like mechanisms we observe today. They're demolition derbies. Protoplanets smashing into each other. Gas giants migrating inward and outward, their gravity flinging smaller objects around like cosmic fastballs. It's estimated that our own solar system ejected billions of objects during its formation, maybe even trillions. Jupiter, that massive striped guardian of the outer solar system, was probably the main culprit in our neighbourhood. Its gravity is so strong that any comet or asteroid that wandered too close got two choices: crash into something or get thrown out of the solar system entirely. No middle ground. Computer simulations suggest that for every object currently in the Kuiper Belt, that distant reservoir of icy bodies beyond Neptune, another 100 were ejected into interstellar space. 100 times more than what remained. Just tossed out. Cosmic refugees. And here's the kicker: every star system probably does this. The red dwarfs with their tightly packed planetary families. The binary star systems where two suns orbit each other, creating gravitational chaos. Even massive O-type stars that burn bright and die young, leaving behind systems in turmoil. All of them creating interstellar wanderers. Dr. Laughlin's team calculated that the Milky Way galaxy should contain approximately 10 circumflex 26 interstellar objects. That's a 1 followed by 26 zeros. For context, that's more than the number of stars in the observable universe, more than the number of grains of sand on every beach on Earth, more than the number of seconds since the Big Bang. Can you picture that? Actually, you can't. Human brains aren't wired to comprehend numbers that large, but try anyway. Close your eyes and imagine an ocean of debris rocks, ice balls, maybe even fragments of shattered planets drifting through the darkness between stars. An invisible swarm so dense that you could theoretically hop from one object to another, like stepping stones across a river. Except the river is the entire galaxy, and we're swimming in it. Now, you might be thinking, okay, But if there are so many of these objects, why have we only found 3? Great question. The answer's equal parts obvious and terrifying. We're blind. Our best telescopes are like trying to spot individual snowflakes in a blizzard while standing inside a well-lit room at night. The darkness of space doesn't emit light shocker. I know so. We can only see objects that either reflect sunlight or glow from their own heat. And 3I/Atlas is tiny in astronomical terms. Current estimates put it at maybe 300 meters across. That's about the length of 3 football fields. Now imagine trying to spot something that small when it's beyond the orbit of Mars. Travelling at cosmic speeds, probably tumbling chaotically. Oh, and it's darker than charcoal because millions of years of interstellar radiation have cooked away any reflective surface it once had. You can't, not with current technology, not unless it does something to announce its presence. That's why 3I/Atlas matters so much. It became active. It started outgassing when it got within 600 million miles of the Sun, creating that thin coma of vapour that made it bright enough to detect. But here's the nightmare fuel: how many interstellar objects passed through our solar system and didn't wake up? How many dark, dormant rocks cruised right past Earth without so much as a how do you do? In 2017, a small asteroid designated 2017 U1 Wait. That sounds familiar? Right. That was Oumuamua's technical name before it got its Hawaiian designation anyway. 2017 U1 wasn't detected until after it passed closest to Earth. We spotted it on its way out. If it had been on a slightly different trajectory, if it had come just a bit closer, we wouldn't have known until impact. Here's what really keeps planetary defense scientists up at night: velocity. A typical near-Earth asteroid hits at about 20 kilometers per second. That's already catastrophic enough energy to level cities, trigger tsunamis, end civilizations. But interstellar objects, they come in at 30, 40, sometimes 50 kilometers per second. The kinetic energy scales with the square of velocity, which means an interstellar impactor carries more than double the destructive force of a regular asteroid of the same size. Dr. Alan Stern, principal investigator of the New Horizons mission, mentioned in a 2020 symposium. The interstellar velocity regime is something we're not prepared for. Detection-wise or defense-wise, these objects give us almost no warning time. And the trajectories. Forget everything you learned about orbital mechanics in school. Solar system objects follow predictable paths. We can calculate where they'll be decades in advance. But interstellar visitors come from any direction, at any time, with no pattern. It's like the difference between traffic on a highway, fast but predictable, and bullets fired randomly from unknown locations. Want to know something that'll really mess with your sleep schedule? Go outside tonight. Look up at the stars. Pick any random point in the sky. Right now, at this very moment, there's probably an interstellar object moving through that exact region of space. You can't see it. No telescope on Earth can see it. But it's there. A silent visitor from another star system, carrying secrets from a place no human will ever visit. And it's not alone. Statistically speaking, based on the 3 confirmed detections we've made and the volume of space we're monitoring, astronomers estimate that there should be at least 1 interstellar object inside Earth's orbit at any given time. 1 right now, somewhere between us and the Sun, or maybe between us and Mars. There's a fragment of another world silently passing through our neighbourhood. Sleep tight. Right. But here's the thing that really gets under my skin about 3I/Atlas specifically. It wasn't just passing through. Its trajectory brought it relatively close to the inner solar system within a few 100 million miles of Earth's orbit. Not threatening, not dangerous, but close enough that if its path had been tilted by just a few degrees, if the timing had been slightly different, well, we might have had a very different conversation. Because when you rewind the math far enough, when you account for all the gravitational nudges and perturbations that 3i/Atlas experienced during its millions of years journey, you realise something profound its arrival here, its appearance in our sky, was determined by events that happened before humans existed, before dinosaurs existed, before animals existed. Some planetary collision in a system dozens of light years away, some gravitational dance between gas giants we'll never observe, set 3i/Atlas on a course that brought it to us in October 2019. The timeline was locked in when our planet was still a molten ball of rock. That's destiny on a cosmic scale. That's determinism that makes human concepts of fate look quaint. And now that we know these visitors exist, now that we've started counting them and tracking them and understanding their trajectories, we have to confront an uncomfortable truth. The universe is far more interconnected than we thought. Star systems aren't isolated islands. They're constantly exchanging material, throwing objects back and forth across the galactic void like some impossibly slow-motion game of catch. Which raises a question that sounds like science fiction but is actually hard science. What else are they exchanging? When 3i/Atlas crossed the threshold into our solar system's gravitational influence, something remarkable happened. The sun's heat began to reach it, warming its ancient surface for the first time in potentially millions of years. And like a frozen body slowly thawing, it started to wake up. This is where the story gets genuinely fascinating and a little creepy. You see, when comets from our own solar system approach the sun, we know exactly what to expect. They've been doing this dance for billions of years. The heat vaporizes surface ice's water, carbon dioxide, methane creating those spectacular glowing tails that have terrified and inspired humans throughout history. We've got the chemistry down to a science. We can predict brightness, tail formation, even the exact compounds they'll release at specific distances from the sun. But 3i/Atlas didn't read our textbook. The first sign that something was different came from spectroscopic analysis. Hang with me here, this isn't as boring as it sounds, I promise. When you split light from a comet into its component wavelengths, you get what's called a spectrum. It's basically a fingerprint showing exactly what chemicals are present in the coma. Every molecule absorbs and emits light at specific wavelengths, creating a unique pattern. Dr. Bryce Bolin from Caltech, who was part of the team analysing 3i/Atlas, noticed something odd in the early data. The CN emission, that's cyanogen, a compound that shows up in most comets, was present but weaker than expected. Meanwhile, the C2 emission's diatomic carbon molecules were slightly elevated. It's like examining someone's DNA and finding familiar sequences arranged in an unfamiliar pattern. The ratio was off, Dr. Bolin noted in his observing report. Not drastically, but enough to make you look twice. Now, before you ask, no, this doesn't mean 3i/Atlas is made of alien chemistry. Carbon is carbon. Cyanogen is cyanogen. The building blocks of the universe are universal, that's literally why we call them that. But the ratios matter. They tell us about temperature, pressure, and chemical conditions during formation. It's the difference between baking a cake at 350 degrees versus 400 degrees. Same ingredients, different results. The fact that 3i/Atlas showed even subtle chemical differences suggests it formed in an environment that wasn't quite like our solar system. Maybe its parent star was cooler. Maybe the protoplanetary disk it condensed from had a different chemical composition. Maybe it formed farther from its star than most of our comets form from the sun. But here's where it gets wild. 3i/Atlas started outgassing at approximately 2.4 AU from the sun. That's astronomical units. 1 AU is the distance from Earth to the sun, about 93 million miles. So we're talking about 223 million miles away. Most comets from our solar system don't really wake up until they get inside 3AU, and some not until they're way closer. Why did 3I/Atlas activate so early? One theory, hypervolatile ices. We're talking about compounds that vaporize at extremely cold temperatures. Carbon monoxide ice, for instance, sublimates at around minus 340 degrees Fahrenheit. That's colder than anything you'd find on Earth, even in the coldest laboratory freezer. If 3I/Atlas had significant amounts of these hypervolatiles on its surface, it would start out gassing while still far from the sun, exactly what we observed. And what does that tell us? That 3I/Atlas spent most of its existence in temperatures even more frigid than the outer reaches of our solar system. Maybe it came from a red dwarf system, where the habitable zone is close to the star and everything beyond is locked in eternal deep freeze. Maybe it wandered interstellar space for so long that cosmic rays and the ambient temperature of space, a balmy minus 454 degrees Fahrenheit, gradually converted its surface into these exotic ices. Dr. Michelle Bannister, a planetary astronomer from the University of Canterbury who's made a career of studying these objects, put it beautifully. Every interstellar visitor is a messenger carrying information about conditions we can't directly observe. They're like finding a message in a bottle, except the ocean is the galaxy and the message is written in chemistry. But let's talk about what really happened when 3I/Atlas woke up. Because this isn't just about dry chemistry and temperature charts. This is about witnessing the awakening of something that travelled farther than any human-made object will reach it in our lifetimes. As solar radiation warmed its surface, ices began to sublimate, turning directly from solid to gas without passing through a liquid phase. Imagine dry ice, but happening across an object the size of a mountain. Jets of vapour started erupting from the surface, likely from specific active regions where the ice was more volatile or where sunlight hit at optimal angles. These jets carried dust particles that had been frozen into the ice matrix, microscopic grains that formed around an alien star billions of years ago. Those dust particles scattered sunlight, making 3I/Atlas visible to our telescopes as a fuzzy blob surrounded by a thin coma. The coma itself expanded as the object approached the sun, growing from perhaps a few thousand kilometers across to tens of thousands. Not nearly as impressive as famous comets like Hale-Bopp or Hyakutake, but considering this was our first chance to watch an active interstellar comet wake up in real time, scientists were glued to their telescopes. And here's something that'll blow your mind: every single dust particle released by 3I/Atlas is now on its own trajectory through the solar system. Some will fall toward the sun, some will be pushed outward by solar radiation pressure. A tiny fraction might even eventually intersect Earth's orbit. Which means, and I want you to really think about this, you might one day watch a meteor shower caused by debris from an interstellar visitor. A shooting star that originated in another star system. How's that for perspective, Doctor? Paul Weissman from the Planetary Science Institute has studied cometary dust for decades. He calculated that a typical active comet releases between 10 and 100 tons of material per second when it's near perihelion closest approach to the sun. 3I/Atlas was less active, probably releasing a few tons per second at most. But even at that rate, over the weeks and months of its passage, it left behind potentially thousands of tons of material. That material is now part of our solar system's inventory. Forever. We absorbed it, claimed it. Like stray cats that wander into your yard and decide to stay, except these particular cats are microscopic dust grains travelling at 30 kilometers per second. But let's zoom in on something specific that happened during 3I/Atlas's awakening, something that really highlights how alien this object was. On November 20th, 2019 observers using the Gemini North Telescope in Hawaii captured detailed images of 3 I/Atlas's coma structure. They were looking for asymmetries, jets, anything that would reveal active regions on the nucleus. What they found was subtle. The coma was relatively symmetric, which suggested either uniform outgassing from all sides or a nucleus that was rotating fast enough to average out any jets. But there was a slight elongation, a gentle stretching of the coma in one direction. This indicated preferential outgassing from one hemisphere of the nucleus. Maybe that side had more volatile ice. Maybe it had a different surface composition. Or maybe, and this is where it gets interesting, maybe that side had been facing interstellar space during its millions of years' journey and had accumulated a different type of surface processing. You see, interstellar space isn't empty. It contains cosmic rays, high-energy particles that slam into objects at nearly the speed of light over millions of years. These cosmic rays can actually change the chemistry of surface ices, creating new compounds that don't form naturally through normal freezing. It's like leaving food in a microwave that runs for a million years. You're going to get some weird results. Scientists call this space weathering, and it's one of the main differences between objects born in our solar system and interstellar wanderers. Our comets spend most of their time in the Kuiper belt, relatively shielded by the sun's magnetic field and the heliosphere, that bubble of solar wind that protects us from the worst of interstellar radiation. But 3 I/Atlas, it spent eons outside that protection, getting bombarded by everything the galaxy could throw at it. When it entered our solar system and the sun's heat started working on its surface, those space-weathered ices behaved differently than normal comet ices. They might have sublimated at unexpected temperatures. They might have released compounds we don't usually see. The chemistry was familiar but foreign, like hearing someone speak English with an accent you can't quite place. Dr. Darrell Seligman from the University of Chicago, who's done extensive modelling of interstellar object behaviour, explained it like this. These objects have been marinating in the interstellar medium for geological timescales. By the time they reach us, their surfaces are archives of processes we can't replicate in laboratories. Think about that. 3 I/Atlas's surface was literally a record of its journey. Every cosmic ray impact, every close pass by another interstellar object, every stray dust grain it encountered, all of it left microscopic scars and chemical signatures. Reading those signatures is like finding an ancient manuscript written in a language we're still learning to decode. And we're getting better at the translation. One of the key breakthroughs came from comparing 3 I/Atlas to 2 I/Borisov. The second interstellar visitor, Borisov, was more active, larger, and we got way more data on it. Its composition looked remarkably similar to solar system comets, lots of water ice, carbon monoxide, cyanogen. But there were subtle differences in isotope ratios. Isotopes are versions of elements with different numbers of neutrons. They behave chemically identical but have slightly different masses. The deuterium to hydrogen ratio in Borisov's water vapor deuterium is heavy hydrogen was measured by multiple teams. It came in at about 2 to 4 times the ratio in Earth's oceans, which is high but not unprecedented. Some comets in our solar system show similar values, but the fact that an object from another star system had water isotopes even remotely similar to ours, that's telling us something profound about galactic chemistry. Water is universal. The processes that create it, that freeze it into comets, that lock it away in icy bodies at the edges of star systems, those processes are universal too. 3 I/Atlas, Borisov, and every other interstellar comet out there are probably made of fundamentally the same stuff as our own cosmic neighbourhood, which sounds comforting. Right, we're all made of star stuff. We're all connected. Cosmic unity and all that. Except here's the thing that should make you deeply uncomfortable if the material is the same everywhere. If comets in distant star systems are basically identical to comets here, then they can carry the same things. And I'm not just talking about water and carbon dioxide. I'm talking about organic molecules, complex chemistry, the building blocks that, under the right conditions, might assemble into something far more interesting than inert ice and rock. In 2019, before 3I/Atlas was even discovered, scientists detected glycine, the simplest amino acid, in samples from the comet 67P/Churyumov-Gerasimenko, visited by the Rosetta spacecraft. Amino acids, the components of proteins, the machinery of life, just hanging out on a comet that's been circling the sun for billions of years. Now ask yourself, if our comets contain amino acids, why wouldn't interstellar comets? And if interstellar comets do contain amino acids, and if billions of these objects have been raining down on planets throughout the galaxy for billions of years, well, that's when the awakening of 3I/Atlas stops being just a cool astronomical event and starts being something else entirely. Something that demands we reconsider not just where we came from, but what's out there, what's always been out there, what might be hitching a ride on these silent messengers from the stars. But before we go down that particular rabbit hole, and trust me, we're going there, we need to confront a more immediate problem: the sheer number of these things. Let's play a game. Actually, let's do some math that'll make you question everything you thought you knew about our place in space. Grab a calculator if you want, or just follow along. This is going to get uncomfortable. In 2017, we discovered Oumuamua, the first confirmed interstellar object. That's one object in 1 year. Then in 2019, we found Borisov. That's 2 objects in 3 years. Then later in 2019, we caught 3I/Atlas. 3 objects in 3 years. Now here's where your brain should start tingling. These weren't found by one telescope dedicating all its time to searching. These were found by sky surveys that spend most of their time looking for near-Earth asteroids, supernovae, variable stars, all sorts of things. The search for interstellar objects that's almost accidental. We're not actively hunting them, we're just happening to spot them when they pass through our field of view. Doctor. Avi Loeb and his colleague Amir Siraj from Harvard ran the numbers in a 2019 paper that should have made international headlines, but mostly just circulated in academic circles. Based on the detection rate and accounting for observational bias, the fact that we can only see objects above a certain brightness, within certain distances, moving at certain speeds, they calculated the density of interstellar objects in our solar system. Ready for this: at any given moment, there are approximately 10,000 interstellar objects within Neptune's orbit. 10,000. Not over the course of a year, not cumulative throughout history, right now. As you're reading this, 10,000 visitors from other star systems are cruising through our cosmic neighbourhood. Let that marinate for a second. The solar system, you thought you knew, the tidy collection of 8 planets, some moons, a bunch of asteroids, and the occasional comet is actually swimming in foreign material. We're not isolated. We never were. But wait, it gets worse. Or better. Depending on your perspective and how much you enjoy existential dread, those 10,000 objects that's just inside Neptune's orbit, about 2.8 billion miles from the Sun. If you extend the calculation to the entire solar system, including the Oort cloud, that vast sphere of icy bodies that extends nearly a light year from the Sun, the numbers become absolutely absurd, Doctor. David Jewett from UCLA, one of the discoverers of the Kuiper Belt, published estimates suggesting there could be more interstellar objects in the outer solar system than native objects. Read that again. More foreigners than locals. Our solar system might be less like a gated community and more like a highway rest stop where travellers outnumber the staff. The Vera Rubin Observatory, which started operations in 2025, is about to confirm or refute these calculations in spectacular fashion. This telescope in Chile has an 8.4-metre primary mirror and can image the entire visible sky every few nights. It's specifically designed to catch transient events, things that move, change, or appear suddenly. Astronomers estimate that once Vera Rubin is at full capacity, it'll detect between 1 and 10 interstellar objects per month, not per year, per month. Within a decade, we might have a catalogue of hundreds or thousands of these visitors, each one a data point telling us something about stellar systems across the galaxy. Dr. Matthew Holman, who works on the Vera Rubin project, said in a 2024 interview. We're about to go from finding interstellar objects being a career-defining discovery to it being just another Tuesday, and I don't think we're emotionally prepared for that shift. He's right. Think about what that means. Right now, 3I/Atlas is special. It's one of only 3 confirmed interstellar visitors. We write papers about it, make videos about it, marvel at its alien origin. But in 5 years, finding an interstellar object will be routine, expected, almost boring, except it won't be boring, because each one will raise the same terrifying question: what else is out there that we can't see? Remember, we only detect these objects when they're bright enough, either reflecting sunlight or glowing from their own outgassing. But what about the dark ones? The inactive rocks with no volatiles to sublimate, no shiny surfaces to reflect light, just dead stone tumbling through the void. In 2018, a small asteroid designated 2018 LA hit Earth over Botswana. We detected it 8 hours before impact. 8 hours. It was only 6 feet across tiny by astronomical standards, but it packed the energy of several tons of TNT. Thankfully, it exploded in the atmosphere, scattering meteorites across the Kalahari Desert that collectors eagerly hunted down afterward. But here's the punchline. 2018 A was one of ours, a regular solar system asteroid on a predictable orbit that happened to intersect Earth. We still only saw it 8 hours before impact. Now imagine an interstellar object on the same trajectory, coming in faster 50% to 100% faster than typical near-Earth asteroids. Darker, because millions of years in interstellar space have cooked its surface into charcoal black regolith. No outgassing to create a visible coma. How much warning will we get? 4 hours too. Maybe none at all if it came from a direction where the sun's glare blinded our telescopes. Dr. Kelly Fast, who manages NASA's Near-Earth Object Observations program, addressed this in a 2023 congressional hearing. She was asked point-blank, if an interstellar object were on a collision course with Earth, how much warning time would we have? Her answer, paraphrased, it depends on size and approach angle, but for anything under 100 meters, we might not detect it until days or hours before impact. Maybe not at all. The representative asking the question looked like someone had just told him his house was on fire, because that's essentially what Dr. Fast said. Our planetary defense system, all those telescopes scanning the sky, all that computational power tracking trajectories is calibrated for solar system objects. Predictable orbits, slow approach speeds. We're watching the front door while the back door is wide open. But let's zoom out even further. Because individual objects, scary as they are, aren't the real horror show. The real horror is the population. Dr. Amaya Morrow-Martin, whose work I mentioned earlier, didn't just study individual interstellar objects, she studied the demographics. How many objects of each size? What's the distribution? And most importantly, where do they all come from? Her team's calculations, published across multiple papers from 2018 to 2024, paint a picture of the galaxy that's simultaneously beautiful and terrifying. Every star system, as it forms, creates a planetary system, and every planetary system during its chaotic youth ejects billions of objects into interstellar space. Gas giants migrate. Planets collide. Gravitational interactions fling comets and asteroids into the void like cosmic buckshot. Our solar system probably contributed 100 billion objects to the interstellar population, maybe a trillion. Most of them small less than a kilometre across, but some potentially much larger. There might be Mars-sized bodies drifting between the stars, ejected during the early chaos of planetary formation, rogue planets with no star to call home, just wandering the galaxy in eternal darkness. And if our solar system did that, so did the other 200 to 400 billion star systems in the Milky Way. Do the math. Actually, don't the numbers are too big? But conceptually, try to wrap your head around this. The galaxy contains more free-floating objects than stars. The space between stars isn't empty, it's full, crowded, a cosmic junkyard of planets, moons, asteroids, and comets that got kicked out of their birth systems and now drift aimlessly through the void. Doctor. Laughlin called it the galactic debris field. Others call it the interstellar ocean. Whatever you call it, we're swimming in it, and we've only just realised the water's there. But here's what really keeps me up at night, and I want you to think about this carefully. If there are trillions upon trillions of these objects drifting through the galaxy, constantly being created by young star systems and constantly wandering into new star systems, then the material of the galaxy is constantly being mixed, redistributed, shared. A comet formed in a star system 500 light-years away might wander for 10 million years and end up here. Another comet from our system might end up 500 light-years in the opposite direction. Over billions of years, over the lifetime of the galaxy, this process has shuffled material across unimaginable distances, which means, and this is where it gets really weird, Earth might contain material from dozens or hundreds of different star systems. Not just primordial material from the molecular cloud that formed the solar system. I'm talking about actual rocks, ice, dust from other stars that wandered in and got captured by the sun's gravity or collided with planets. In 2014, researchers claimed to have found the first meteorite of interstellar origin, a fragment recovered from a Papua New Guinea fireball that showed peculiar isotopic signatures. The claim is disputed, the data is messy, but the implication is clear interstellar material does hit Earth. Probably has been hitting Earth for billions of years. Every time you walk on a beach, some of those sand grains might be from another star system. Every time it rains, some of those water molecules might have once been part of a comet that formed around a star that died before our sun was born. You are quite literally made of stardust. But not just our star's dust. You're made of the galaxy, atoms from across the Milky Way, mixed and remixed and eventually assembled into you. How's that for perspective? But before you get too comfortable with that cosmic poetry, remember, if material can travel between star systems, so can other things. Chemistry, complex molecules, maybe even biology, the theory of panspermia. The idea that life could spread between star systems via comets and asteroids has been around since the 1800s. Scientists like Fred Hoyle and Chandra Wickramasinghe argued that comets could carry microorganisms across interstellar space, seeding planets with life wherever they landed. Most scientists dismissed this as fringe science. Too unlikely, too speculative. Life couldn't survive millions of years in the radiation-soaked void of space. Except we keep finding evidence that maybe it could. In 2007, researchers exposed bacteria to the vacuum of space aboard the International Space Station. Bacillus subtilis spores survived for 18 months with minimal shielding. In 2011, researchers found that certain extremophile bacteria could survive simulated interstellar conditions, vacuum radiation, temperature extremes for years. And in 2020, scientists discovered that amino acids, complex organic molecules, are common in comets. Not just simple stuff. We're talking about the building blocks of proteins. So let's connect the dots. Comets contain organic molecules. Comets get ejected from star systems by the billions. Those comets wander the galaxy for millions of years. Eventually, some of them crash into planets. And we know microorganisms can survive in space for extended periods if protected inside rock or ice. The logical conclusion, life might not be confined to individual planets or even individual star systems. Life might be a galactic phenomenon, constantly spreading, constantly seeding new worlds, using interstellar objects as vessels, which means 3I/Atlas, that small, seemingly insignificant comet that passed through our solar system in 2019 might have been more than just a rock. It might have been an ark, a seed pod, a messenger carrying something far more significant than water, ice and dust. And if that's true, if interstellar objects regularly carry organic material or even life between star systems, then the next question is unavoidable: what has already been delivered to Earth? What's growing here that came from somewhere else? And what are we sending out into the galaxy every time our own solar system ejects something into interstellar space? The big picture isn't just terrifying because of the numbers. It's terrifying because of what those numbers mean. We're not isolated. We're not special. We're just one port in a vast network of material exchange that's been operating for billions of years. And we're only just now beginning to read the shipping manifests. You can't see them. That's the part that should terrify you more than anything else. Right now, as you're reading this, imagine standing in a completely dark room. The kind of darkness where you can't see your hand in front of your face. And someone tells you that room is filled with furniture chairs, tables, shelves, sharp corners, thousands of pieces scattered randomly throughout the space. But you have no flashlight, no night vision, just your outstretched hands and the hope that you don't walk face first into something hard. That's us. That's humanity trying to detect interstellar objects. Let me break down exactly how blind we really are. Our best guy surveys the ones that found 3I/Atlas. Borisov and Oumuamua can detect objects down to about magnitude 22. In astronomy, magnitude is a backwards scale where smaller numbers mean brighter objects. The sun is magnitude -27, the full moon is -13. The faintest stars you can see with your naked eye are about magnitude 6. And magnitude 22, that's roughly 10 million times fainter than what your eyes can see. Sounds impressive. Right. We can detect objects 10 million times fainter than naked eye visibility. We're basically cosmic superheroes with X-ray vision. Except here's the problem: space is really, really big, and objects in space are really, really small. And they don't glow on their own, they only reflect sunlight. And the amount of sunlight they reflect depends on their size, distance, and how reflective their surface is. Let's do some real calculations. Take 3I/Atlas. It's estimated to be about 300 meters across roughly 3 football fields. When it was discovered, it was about 2.5 AU from the Sun, about 230 million miles. At that distance, with its estimated size and albedo, that's reflectivity, it was barely bright enough to be detected by Atlas, which is literally designed for this stuff. Now imagine 3I/Atlas was just 50% farther away, or 50% smaller, or had a darker surface. We wouldn't have seen it. It would have passed through our solar system completely unnoticed, like a submarine running silent through enemy waters. Dr. Robert Werrick, who was part of the team that discovered Oumuamua, explained the detection challenge in a 2018 interview. We're basically looking for a moving needle in a haystack of non-moving needles. And the moving needle only shows up for a few nights before it's too faint to see again. Because that's the other problem: these objects move fast. Oumuamua was visible for about 3 weeks before it faded below detection threshold. Borisov lasted longer because we caught it earlier, but it was still a race against time to get telescope observations scheduled before it disappeared. 3 Ice/Atlas astronomers had maybe a few months of useful observation time before it became too faint to study. It's like trying to photograph a speeding bullet at night using only the glint of moonlight reflecting off its surface. And you'd only get one shot. Miss it, and it's gone forever. But let's talk about what we're not seeing, because this is where it gets genuinely scary. In 2019, Dr. Milena Rice from Yale University published a fascinating paper. She calculated the detection probability for interstellar objects based on their approach angle, size, and velocity. Her conclusions: we're missing approximately 99.9% of interstellar objects that pass through the solar system. Read that again. For every one object we detect, there are roughly 1,000 that slip past unnoticed. Why? Because our sky surveys have something called cadence. How often they look at the same patch of sky. Most surveys revisit the same region every few nights or weeks, but interstellar objects move across the sky in days or even hours. If a survey happens to be looking at a different part of the sky when an object passes through, that object remains invisible. It's like having a security camera that only takes a photo every 5 minutes. Sure, you'll catch some people walking through your yard, but you'll miss most of them. Now imagine those people are travelling at highway speeds. You'll miss almost all of them, and that's just the objects big enough and bright enough to be detected in the first place. What about the small ones, the dark ones, the ones that don't outgas and create a convenient coma to make them brighter? In 2017, just before Oumuamua was discovered, Dr. Gregory Laughlin calculated that at any given moment, there should be at least one interstellar object within 1 AU of Earth that's roughly the distance from Earth to the Sun, about 93 million miles. Not within Neptune's orbit, not in the outer solar system, within Earth's orbit, close. One object, on average, could be larger than average, could be smaller, could be closer, could be farther. But statistically, right now, there's an interstellar visitor nearby, and we have no idea where it is. Want to know something even more disturbing? In 2013, 4 years before Oumuamua was discovered, a small meteor exploded over Chelyabinsk, Russia. The shockwave blew out windows across the city, injured over 1,500 people, and released energy equivalent to about 30 Hiroshima bombs. The object was only 20 meters across, and we didn't see it coming. Zero warning, it approached from the direction of the sun, where telescopes are essentially blind because, the sun is bright. Now, that meteor was almost certainly a regular near-Earth asteroid, not an interstellar visitor. But here's the thought that keeps planetary defense scientists awake at night. What if it had been interstellar, same size, same approach angle, but travelling 50% faster due to its hyperbolic trajectory? The energy release would have been significantly larger. The damage would have been catastrophic. And we still wouldn't have seen it coming. Dr. Linley Johnson, who served as NASA's Planetary Defense Officer. Yes, that's a real job title. And yes, it's both cool and terrifying addressed this scenario in a 2020 congressional testimony. His assessment: our current detection systems are optimized for objects on elliptical orbits with relatively predictable trajectories. Interstellar objects represent a different challenge entirely. Faster velocities, random approach angles, potentially darker surfaces, all of these factors reduce our detection capability. Translation: if a dangerous interstellar object is heading toward Earth, we might not know until it's already here. But wait, it gets even worse. Because everything I've told you so far assumes the object is reflecting sunlight. What if it's not? In 2020, astronomers discovered an object designated 2020 so. Initial observations suggested it might be a small asteroid, or even an interstellar visitor because its orbit looked weird. After weeks of analysis, they figured out what it actually was: the Centaur upper stage rocket from the Surveyor 2 mission, launched in 1966, a piece of human space junk that had wandered into a distant orbit and was now returning to Earth. The point: even we struggled to identify a man-made object that we knew existed, that we had records of, that we launched ourselves, and that was only 10 meters across and relatively reflective. Now, imagine an interstellar object that's naturally dark. Some asteroids, particularly carbonaceous chondrites, have albedos as low as 0. 0.3, they reflect only 3% of the light that hits them. That's darker than asphalt, darker than charcoal, approaching the blackness of fresh printer toner. If an object like that passed through the inner solar system even relatively close to Earth, we might never see it. It would be like trying to spot a black cat in a dark room while wearing sunglasses. Dr. Alan Harris from the Space Science Institute calculated that we're probably missing 90% of potentially hazardous asteroids smaller than 140 meters. And those are native objects that we've had billions of years to catalogue interstellar objects. The detection rate is probably much worse. So, let's play a little thought experiment. Humour me. Imagine you're standing in a field at night. It's a clear night, no moon, just stars overhead. Beautiful and peaceful. Now, imagine someone tells you that every minute a bullet passes through that field, sometimes high overhead, sometimes closer to the ground. Completely random trajectories, completely random timing, and you can't see them, can't hear them, can't detect them in any way. How comfortable are you standing in that field now? That's Earth, that's where you live. Except instead of bullets, it's asteroids, comets, and interstellar visitors. Instead of every minute, it's, well, we don't actually know the frequency. Could be every few years, could be multiple times per year. And instead of a field, it's the entire volume of space around Earth. Sleep tight. But here's the really insidious part. The objects we can't see might be more common than the objects we can see. Think about it. The only reason we detected 3I/Atlas was because it started out gassing. It became active, created a coma, got brighter. But what about interstellar visitors that don't have volatile ices, rocky asteroids, that have been baked by cosmic radiation for millions of years? All the volatiles long since boiled away. Dr. Darrell Seligman from the University of Chicago published a paper in 2020 suggesting that for every active interstellar comet we detect, there might be 10 to 100 inactive rocky interstellar asteroids that pass through unnoticed. They're darker, smaller, and don't conveniently announce their presence by glowing. We've likely been visited by hundreds or thousands of interstellar asteroids that we never detected. Dr. Seligman wrote, "They're the dark fleet, and we're essentially blind to them." The dark fleet, I love that term. It's both poetic and absolutely horrifying. And it's not just about asteroids that might hit us, though. That's certainly a concern. It's about the fact that we're trying to understand the population of interstellar objects, trying to calculate how many there are and where they come from. But we're working with a sample size that's ridiculously biased. It's like trying to understand ocean life by only studying whales and dolphins, the big, charismatic megafauna that we can easily spot from boats. Meanwhile, there are billions of smaller fish, countless invertebrates. Entire ecosystems were completely missing because they're below the surface. Too small, too dark, too fast. In 2021, a team led by Dr. Amir Siraj from Harvard estimated that the Vera Rubin Observatory, once fully operational, would detect between 1 and 10 interstellar objects per month. But even those numbers are just the tip of the iceberg. For every object Vera Rubin detects, there will be hundreds or thousands that remain invisible. The observatory will revolutionize our understanding. Don't get me wrong. Going from 3 known interstellar objects to potentially hundreds within a few years, that's incredible. We'll finally have enough data to study the population statistically, to understand size distributions, compositional variations, orbital characteristics. But even Vera Rubin has limits. It can only detect objects down to magnitude 24. 5 better than current surveys, but still nowhere near sensitive enough to catch the small, dark objects that probably make up the majority of the interstellar population. Dr. Matthew Holman, who works on the Vera Rubin project, put it bluntly in a 2024 interview. We're about to go from essentially blind to nearsighted. It's a huge improvement, but let's not pretend we'll be seeing the full picture. So, what's the solution? How do we actually detect these dark objects before they sneak up on us? Some researchers are proposing space-based infrared telescopes. Infrared sees heat, and even cold objects in space emit some thermal radiation. An infrared survey could potentially detect asteroids that are invisible in visible light. NASA's proposed NEO Surveyor mission, if it ever gets fully funded and launched, could do exactly this. Others suggest expanding ground-based surveys, more telescopes, faster cadence, better algorithms to identify moving objects in real time. The technology exists. It's mostly a funding issue. But here's the uncomfortable truth, even with all the money in the world. Even with 100 telescopes scanning the sky 24/7, we're still going to miss objects. The solar system is just too big. The objects are too small. The problem is fundamentally unsolvable with current technology. Unless... And here's where it gets interesting. Unless we change our approach entirely, what if instead of trying to see interstellar objects from Earth, we send detectors out into space? Small satellites in solar orbit, spread throughout the inner solar system, each one acting as an early warning system. They wouldn't need to be sophisticated, just sensitive enough to detect approaching objects and radio their findings back to Earth. Dr. Philip Lubin from UC Santa Barbara has proposed exactly this concept. He calls it the Sentinel Network, hundreds of small, cheap satellites forming a detection grid. When an object passes near any satellite, that satellite pings the network, and suddenly we have a 3D trajectory, time to impact, size estimate, everything we need to. Well, to at least know it's coming. Would we be able to do anything about it? That's a different question. But knowledge is better than ignorance. The depressing reality is that this network doesn't exist. It's not funded. It's not even in serious planning stages. We're essentially waiting for something bad to happen before we invest in the infrastructure to prevent it from happening again. Which brings us back to 3I/Atlas. That small, active comet that we happened to spot because it was kind enough to start outgassing at the right time, in the right place, when the right telescope was looking in the right direction. How many others like it passed through while we weren't looking? How many darker, deadlier cousins are out there right now? Invisible ghosts in the machine, wandering through our cosmic neighborhood with no one to witness their passage. The answer is, we don't know. And that might be the most terrifying answer of all. So where did it come from? That's the question that haunts astronomers every time they detect an interstellar visitor. Because unlike objects born in our solar system where we can trace their orbits backward and forward with precision, where we know they've been circling the sun for billions of years, interstellar objects are mysteries wrapped in math problems, wrapped in cosmic uncertainty. With 3I/Atlas, researchers did what they always do, they reversed the trajectory. They took the position, velocity and direction data from dozens of observations, fed it into orbital dynamics software, and pressed rewind on the universe. The object came from the direction of the constellation Ursa Major the Great Bear, home to the Big Dipper. That much was clear. But constellations are just patterns we see from Earth. They don't mean anything in three-dimensional space. Stars that look close together from our perspective might be hundreds of light years apart. So the team kept rewinding. They accounted for the sun's motion through the galaxy. We're not stationary. After all, the entire solar system is orbiting the galactic center at about 514,000 miles per hour, completing one lap every 230 million years. They accounted for the gravitational influence of nearby stars, the slight perturbations from planets, even the barely measurable effects of solar radiation pressure, and they traced 3I/Atlas's path backward through space and time, 4 million years ago, give or take. 3I/Atlas was somewhere else. The calculations get fuzzy that far back because small uncertainties in current measurements compound exponentially when you're rewinding millions of years. It's like trying to figure out where a leaf in a river came from by watching where it goes possible in theory. But chaos theory makes it increasingly uncertain the farther back you look. But the team could narrow it down to a region of space. And what they found was frustratingly nothing definitive. No obvious stellar candidate, no nearby star that 3I/Atlas clearly originated from. Dr. Quanzi Ye, who led the analysis, published his findings with appropriate scientific caution. The trajectory suggests an origin from a stellar system within approximately 100 light-years. But we cannot identify a specific source star with confidence. Translation, it came from somewhere relatively nearby in galactic terms, but space is so vast that nearby still contains thousands of potential candidates. Let that sink in for a moment. We can detect an object hurtling through space at cosmic speeds. We can measure its composition, track its motion, watch it wake up as sunlight touches its ancient surface. But we can't definitively tell you where it was born. It's like finding a message in a bottle washed up on a beach. You can analyse the bottle, read the message, test the paper and ink, but figuring out which ocean it came from, which beach it was thrown from, who wrote it, that's nearly impossible without additional information. But let's talk about what we can deduce. Because even though we don't know the specific star system, we can make educated guesses about what kind of place 3I/Atlas came from. First, the composition. Remember that early activation we discussed, the fact that 3I/Atlas started outgassing at 2.4 AU, farther from the Sun than most comets. That tells us it formed in an extremely cold environment. We're talking about temperatures where carbon monoxide ice, which vaporizes at minus 340 degrees Fahrenheit, could remain stable for billions of years. In our solar system, that kind of environment exists in the Kuiper Belt and beyond, but different star systems have different architectures. A red dwarf star, for example, the most common type of star in the galaxy, puts out far less heat than our Sun. The habitable zone around a red dwarf might be closer to the star than Mercury is to the Sun, which means everything beyond that is locked in perpetual deep freeze. Dr. Michelle Bannister suggested in a 2020 paper that 3I/Atlas might have originated from a red dwarf system. The chemistry and activation distance are consistent with formation in an exceptionally cold environment, potentially around an M-class star where the frost line is much closer in and the outer system is a deep freezer. But here's where it gets dark literally and figuratively. Because if 3I/Atlas came from a red dwarf system, that means it might be carrying evidence of something truly catastrophic. Red dwarf systems are violent places, especially when they're young. These stars are prone to massive flares, eruptions of radiation, and charged particles that can strip atmospheres from nearby planets and sterilize anything that might be living there. And their planetary systems are often tightly packed, with multiple worlds orbiting closer than Mercury orbits our Sun. Tight orbits mean strong gravitational interactions, planets pulling on each other. Perturbing orbits, occasionally destabilizing the entire system in a cascade of chaos. It's not uncommon for young red dwarf systems to eject planets entirely full-sized worlds, not just comets and asteroids, thrown out into interstellar space to wander alone forever. So here's a possibility that should make you uncomfortable. 3I/8Ls might be a fragment of a destroyed world. Not just ejected during normal planetary formation, but literally torn apart. Imagine a planet, maybe an ice giant like Neptune, or a super-Earth with a thick icy crust orbiting too close to its star, or another massive planet. Tidal forces start pulling at it, stretching and compressing it like a stress ball. Over time, these forces don't just heat the planet, they can actually rip it apart. We call this tidal disruption, and we've observed it happening to comets that pass too close to Jupiter or the Sun. When a world breaks apart, it creates a debris field. Thousands or millions of fragments, each one carrying the chemical signature of the original body, each one now on its own trajectory, some falling into the star, others ejected into interstellar space at high velocity. 3I/Atlas could be one of those fragments, a piece of a world that died millions of years ago in a star system we can't even identify. And now it's here. A cosmic refugee carrying the chemical memory of Apocalypse Doctor. Sean Raymond from the Laboratoire d'Astrophysique de Bordeaux has spent years simulating planetary system evolution. His models show that violent ejections aren't rare, they're the norm. Every planetary system goes through a phase of dynamical instability, he explained in a 2021 interview. Planets migrate, collide, get ejected. It's messy and violent, and it leaves behind a trail of debris that spreads across the galaxy. So, when you look at 3I/Atlas, you're not just looking at a comet, you're looking at evidence of destruction. Proof that somewhere in the galaxy, something terrible happened. A world ended, a system fell into chaos, and the remnants are still drifting through space, occasionally passing through other star systems, silent witnesses to ancient catastrophe. But let's consider another possibility, one that's less violent but perhaps more unsettling. What if 3I/Atlas wasn't ejected during a catastrophic event? What if it simply drifted away in the outer reaches of every star system? There's a point where the star's gravity becomes too weak to hold on to objects permanently. These distant regions, like our own Oort cloud, are barely bound to the star at all. Any passing perturbation, a rogue planet, a distant stellar encounter, even the gentle tug of the galactic tide can nudge objects in this region just enough to push them over the edge. And then they're gone. Not thrown out violently, but gently released, like helium balloons slipping from a child's hand. They drift away at relatively low velocities, slowly picking up speed as they fall through the galaxy's gravitational field, eventually becoming part of the interstellar background population. Dr. Suzanne Falzner from the Max Planck Institute for Radio Astronomy has studied these gentle ejections. Her calculations suggest that over billions of years, every star system loses a significant fraction of its outermost objects this way. It's not dramatic, she noted. It's just statistics and gravity, but over time, it adds up to an enormous population of free-floating objects. If 3I/Atlas was one of these gentle releases, it might have spent billions of years drifting through the galaxy before encountering our solar system. Billions of years in the cold, in the dark, preserved like a fossil in the deep freeze of space. And here's the really weird part: during that time, it would have been exposed to cosmic rays' high-energy particles that can actually change the chemistry of surface materials. We talked about space weathering before, but let me get more specific about what that means. Cosmic rays don't just bounce off surfaces, they penetrate. At the molecular level, they break chemical bonds, create free radicals, enable reactions that wouldn't normally happen at such low temperatures. Over millions of years, this process can create a surface layer of material that's chemically distinct from the interior. So when 3I/Atlas entered our solar system and started to warm up, the first materials to vaporize were potentially products of millions of years of radiation chemistry. We were essentially watching the unwrapping of a time capsule, seeing the outer layers peel away to reveal progressively older and more pristine material underneath. Dr. Darrell Seligman and his colleagues modelled this process in a 2021 paper. They showed that the spectrum of an interstellar comet should change as it approaches the Sun, not just getting brighter, but actually showing different chemical signatures as different layers sublimate away. Did we observe that with 3I/Atlas? Honestly, the data isn't good enough to say for certain. We didn't get enough high-quality spectra across a wide enough range of distances, but the possibility is there, archived in the observations, waiting for someone to dig deeper, which brings us to a profound and slightly depressing realization: we might never know where 3I/Atlas came from. Not because the information doesn't exist, but because the universe is too big and too old for us to trace backward with certainty. Think about it. If 3I/Atlas has been wandering for 4 million years, the star it originated from has also been moving for 4 million years. Stars don't stay still. They orbit the galactic center just like our sun does, but not in formation like planes in a squadron. Each star has its own velocity, its own trajectory, over millions of years. Stellar neighborhoods completely rearrange themselves. The star that 3I/Atlas came from might now be 200 light-years away in a completely different direction. And unless that star has something distinctive about it, unusual composition, strange motion, some kind of telltale signature, we'll never be able to pick it out of the millions of stellar candidates. It's like trying to figure out which specific tree a leaf fell from after it's been carried by wind and water across an entire continent. The information is theoretically encoded in the leaf's DNA, but good luck extracting and interpreting it. But here's what keeps me up at night: the uncertainty about 3I/Atlas's origin isn't just an academic curiosity. It's a fundamental limitation of our ability to understand the galaxy we live in. Every interstellar object is a data point, a sample from a stellar system we can't directly observe. And we're trying to use these samples to understand galactic chemistry, planetary formation processes, the demographics of planetary systems across the Milky Way. But if we can't trace the samples back to their source, we're essentially studying a massive collection of unlabeled specimens. Imagine a scientist trying to understand biodiversity on Earth. But all the samples they receive are unlabeled. They can study the DNA, analyze the biochemistry, compare morphology, but without knowing where each sample came from: tropical rainforest or Arctic tundra, deep ocean or mountain peak, the big picture understanding remains frustratingly incomplete. That's where we are with interstellar objects. Rich data, limited context. Unless, and here's where it gets interesting again, unless we find multiple objects from the same source system. Think about it. If a star system underwent a major instability event, a planetary collision, a close stellar flyby, a migration of giant planets, it would have ejected thousands or millions of objects all at roughly the same time. Those objects would now be spread across a large volume of space. But they'd share similar trajectories, compositions, and ages. If we could identify multiple interstellar visitors with matching characteristics, we could potentially trace them back to a common origin. It would be like finding puzzle pieces from the same image scattered across a room. Dr. David Jewett proposed exactly this approach in a 2022 paper. He called it forensic astronomy, using the population of interstellar objects to reconstruct events that happened millions of years ago in star systems we can barely see. But here's the catch: we'd need to detect dozens or hundreds of interstellar objects to have enough data for statistical matching. And remember, we've only found 3. Vera Rubin Observatory will help, but even then, we're years away from having a large enough sample size. So, for now, 3I/Atlas remains an enigma, a messenger from nowhere, a fragment of a world that might have been destroyed, or might have simply drifted away, carrying chemistry that hints at its origin but refuses to give up its secrets completely. And the most unsettling part, there's a non-zero chance that 3I/Atlas came from a star system that hosted life. Maybe not on the same body that became 3I/Atlas. It's a comet, after all, formed in the cold outer reaches of its birth system. But the star system itself, the inner planets, we have no way of knowing. For all we know, 3I/Atlas is carrying dust that once drifted through an alien sky, water molecules that once fell as rain on another world, carbon atoms that were once part of something living. That's not science fiction, that's just statistics and chemistry. Life, or at least organic chemistry, is probably common in the galaxy. And if it's common, then some fraction of interstellar objects must carry traces of it. The question isn't whether such objects exist. The question is, have we already encountered one and just didn't look closely enough? Because here's the terrifying truth: we let 3I/Atlas slip away without fully investigating it. We took some spectra, some images, calculated its orbit, but we didn't send a probe to meet it, we didn't collect samples, we didn't analyze its surface composition in detail, and now it's gone, fading into the outer solar system, never to return. Whatever secrets it carried, whatever story it could have told about its origin, are lost to us forever. Unless, of course, it left something behind. Let's talk about what happens when math meets nightmare fuel. You're sitting at home, maybe you're reading this on your phone, maybe on a laptop, comfortable, safe. The walls around you feel solid, the ground beneath you feels stable. Everything in your immediate environment suggests permanence, security, predictability. Now let me tell you what the math says about an interstellar impact. In 2019, shortly after 3I/Atlas was discovered, a group of researchers led by Dr. Amir Siraj decided to run some calculations that nobody really wanted to think about. Not because the math was hard, it wasn't, but because the implications were the kind that make planetary defense scientists reach for strong coffee at 2 a.m. The question was simple. What would happen if an object like 3I/Atlas hit Earth? Let's start with the basics. When astronomers talk about impact energy, they usually reference the Chicxulub impactor, the asteroid that killed the dinosaurs 66 million years ago. That object was roughly 10 kilometers across, hit at approximately 20 kilometers per second, and released energy equivalent to about 100 million megatons of TNT. For context, the largest nuclear weapon ever detonated, the Soviet Tsar bomber, was 50 megatons, so we're talking about 2 million Tsar bombers going off simultaneously. The impact vaporized the asteroid, excavated a crater 150 kilometers wide, triggered global wildfires, generated mega tsunamis, and threw so much debris into the atmosphere that it blocked out the sun for years. The resulting climate change wiped out roughly 75% of all species on Earth. That's the benchmark. That's the disaster scenario we use for comparison. Now, 3I/Atlas is much smaller, maybe 300 meters across, versus Chicxulub's 10,000 meters. So you might think, okay, it's tiny by comparison, no big deal, right? Wrong. Catastrophically wrong. Because here's what most people don't understand about impact physics, energy scales with mass and velocity. Specifically, kinetic energy equals 1/2 mass times velocity squared. That squared part is critical. It means that if you double the velocity, you quadruple the energy. Typical near-Earth asteroids hit at about 20 kilometers per second. We've known this for decades. Our entire planetary defense strategy, such as it is calibrated for those velocities. We calculate Torino-scale ratings. We model deflection missions. We plan evacuation zones. All based on that 20 kilometers per s baseline. Interstellar objects hit at 30 to 50 kilometers per second, sometimes faster. Let's be conservative and say 3I/Atlas would hit at 40 kilometers per s, double the velocity of a typical asteroid. Same mass, double the velocity, means 4 times the energy. An object that would normally release 1 megaton now releases 4 megatons. An object that would have created a local disaster now creates a regional catastrophe. Doctor. Siraj's team calculated that a 300-meter interstellar object impacting at 40 kilometers per s would release approximately 5000 megatons of energy. That's 100 Tsar bombers. Not dinosaur killer level, but absolutely civilization threatening depending on where it hit. Let me paint you a picture of what that actually means. Imagine the impact site is somewhere in the Atlantic Ocean, let's say 1,000 miles off the coast of New York. The object punches through the atmosphere in seconds. There's barely any ablation because it's moving so fast that atmospheric friction doesn't have time to slow it down significantly. It hits the water like a bullet through tissue paper. The ocean is instantly vaporized in a sphere hundreds of meters wide. The shockwave propagates through the water faster than sound, creating an underwater blast wave that would pulverize anything within miles. But that's not the scary part. The scary part is what happens next. The impact crater, even though it's in water, excavates down to the seafloor, potentially several kilometers deep. Millions of tons of water and seafloor material are thrown upward and outward at supersonic speeds. Some of this material reaches escape velocity and actually leaves Earth's atmosphere. The rest comes crashing back down as a rain of superheated rock and steam. But the tsunamis, that's what would kill most people. Dr. Stephen Ward from UC Santa Cruz has spent years modelling asteroid impact tsunamis. His calculations show that a 300-meter impactor in deep ocean would generate waves 100 meters high near the impact site. Those waves would radiate outward in all directions, losing height as they spread but gaining terrifying reach. By the time they reached the US East Coast roughly 500 kilometers away, the waves would still be 30 to 50 meters high. That's a 10 to 15-story building of water moving at highway speeds, and unlike normal tsunamis from earthquakes, which come as a series of waves with gaps in between, an impact tsunami arrives as a single massive surge. New York, Boston, Washington DC, Miami, every coastal city from Maine to Florida would be hit within hours of impact. Evacuation would be nearly impossible because by the time you detect the object, calculate its trajectory, and sound the alarm, you'd have maybe hours of warning, maybe less. The waves would penetrate inland for miles. Everything within 10 kilometers of the coast would be scoured clean. The death toll would be measured in millions. The economic damage would be incalculable. The entire eastern seaboard of the United States would be transformed into a disaster zone that would take decades to recover from. And that's just the immediate impact zone. The atmospheric effects would be global. 5,000 megatons of energy doesn't just create a crater. And tsunamis, it throws an enormous amount of material into the upper atmosphere. Dust, water vapor, vaporized rock. This material would spread around the planet within weeks, blocking sunlight and dropping global temperatures. Dr. Natasha Artemieva from the Planetary Science Institute has modelled the climatic effects of various impact scenarios. Her calculations suggest that a 300-metre impactor would inject enough material into the stratosphere to reduce global temperatures by 3 degrees Celsius for several years. That might not sound like much, but consider the Little Ice Age, that period from the 14th to 19th centuries when the Thames River regularly froze solid and crop failures triggered famines across Europe, was caused by a temperature drop of only about 1 degree Celsius. A 2-3 degree drop would devastate agriculture worldwide. Growing seasons would shorten, frost would come earlier, last longer, crops would fail across the northern hemisphere. We're talking about potential famine affecting billions of people. And remember, this is for a relatively small interstellar object, something the size of 3 football fields, not a dinosaur killer, just a civilization shaker. Now let's talk about the part that really keeps planetary defense scientists awake at night. We probably wouldn't be able to stop it. In September 2022, NASA successfully completed the DART mission Double Asteroid Redirection Test. They deliberately crashed a spacecraft into a small asteroid moon called Dimorphos and successfully altered its orbit. It was humanity's first demonstration of kinetic impactor technology, basically hitting an asteroid with a fast-moving spacecraft to nudge it off course. The mission was hailed as a major success, and rightly so. It proved that we can deflect asteroids if we detect them early enough. But here's the catch: DART worked because Dimorphos was moving at typical solar system velocities. The deflection calculations were based on known orbital mechanics, and crucially, we had years of advance warning to plan and execute the mission. An interstellar impactor changes all the variables. First, the velocity difference. The DART spacecraft hit Dimorphos at about 6.6 km/s relative velocity. An interstellar object would be moving at 30 to 50 km/s. To achieve the same deflection effect, you'd need to hit it with proportionally more force. That means a bigger spacecraft, more fuel, longer preparation time. Second, the trajectory. Solar system asteroids follow predictable elliptical orbits. Even if we only observe them for a few weeks, we can calculate where they'll be months or years in advance with high precision. Interstellar objects, they're on hyperbolic trajectories. They are only in our neighbourhood for weeks or months total. The detection to impact timeline might be measured in days. Dr. Brent Barbee from NASA Goddard has modelled various deflection scenarios for interstellar impactors. His conclusion, published in a 2023 paper, was sobering. For fast-moving interstellar objects detected with less than 1 year of warning time, our current deflection capabilities are insufficient. We simply cannot mount an effective kinetic impactor mission in that time frame. 1 year, that's the cutoff. Less than a year of warning, and we're basically helpless. And remember what we discussed earlier about detection capabilities. Most interstellar objects would give us far less than a year of warning, more like weeks or months, maybe days if they're small and dark. So what are the options if we detect an interstellar impactor on a collision course with Earth? Option 1, nuclear deflection. Detonate a nuclear warhead near the object to vaporize surface material and create thrust that nudges it off course. Sounds like science fiction, but it's actually one of our most realistic options for short warning scenarios. The problem, it's never been tested. We have no idea if it would actually work. And even if it did, mounting a nuclear-armed interception mission in weeks or months would require international cooperation on a scale we've never achieved. Plus, there's the little issue that exploding a nuke in space is technically banned under the Outer Space Treaty of 1967. Yes, even for planetary defense, the treaty would need to be amended or suspended, which requires diplomatic negotiations at exactly the moment when we should be moving fast, Option 2, evacuation. If we can't stop it, at least we can get people out of the impact zone. Except evacuation of millions of people requires weeks or months of preparation. Moving that many people, providing shelter and food, maintaining order, it's a logistical nightmare even in the best circumstances. With only days of warning, it becomes impossible. Dr. Kathy Plesko from Los Alamos National Laboratory ran simulations of emergency evacuations for various impact scenarios. Her findings: effective evacuation requires a minimum of 2 weeks of advance notice, and that's assuming perfect coordination and public cooperation. Realistically, you need a month or more. We probably wouldn't have a month. Option 3, bunker down and hope the impact site isn't near a major population centre. This is basically the do-nothing option, and it's disturbingly likely to be what actually happens in a short warning scenario. We detect the object, calculate the impact site, sound the alarm, and then wait and hope. Hope that it hits ocean instead of land. Hope that it misses populated areas. Hope that the global effects aren't as bad as the models predict. It's not a plan, it's a prayer. But here's what really gets under my skin about all of this: these scenarios aren't hypothetical. They're not academic exercises designed to scare students or secure grant funding. They're based on real physics, real detection limitations, and real orbital mechanics. And 3I/Atlas proved that interstellar objects do visit us. They're real. They're out there. And some of them are definitely on trajectories that will eventually intersect with planets. Dr. Alan Harris, who spent decades studying impact hazards, put it bluntly in a 2020 conference. We've been lucky so far. The interstellar objects we've detected weren't on collision courses, but statistically, it's only a matter of time, and when it happens, we probably won't be ready. Matter of time. That phrase should haunt you, because somewhere in the galaxy right now, there's an object. Maybe it's a rock, maybe it's ice, maybe it's a fragment of a destroyed planet, and it's moving. Silent, invisible, following a trajectory calculated by gravity and chaos millions of years ago. And maybe, just maybe, that trajectory intersects with Earth. Maybe it'll arrive next year. Maybe in 100 years. Maybe in 10,000 years. The math is merciless and doesn't care about our hopes or plans or whether we're ready. And the horrifying truth is that we might not see it until it's already here. Until someone at an observatory catches a glimpse of something moving wrong, calculates its velocity, runs the trajectory, and realizes with cold certainty that there's not enough time to mount a deflection mission, not enough time for effective evacuation, not enough time for anything except watching the numbers count down and hoping the impact site is somewhere, anywhere that minimizes casualties. That's the collision scenario. That's what the math tells us could happen. Not will happen, could. The probability is low, but it's not zero. And every time we detect another interstellar object, every time we refine our population estimates and realize there are more of them than we thought, that probability ticks upward. Still feeling safe behind those walls. Still think the ground beneath you is stable, because here's what 3I/Atlas really taught us: the universe doesn't need malice to be dangerous. It doesn't need intent or purpose. It just needs physics and probability and time. And we've got plenty of all three. Now let's talk about something that sounds like science fiction, but is actually just science: the possibility that 3I/Atlas carried passengers, not little green men, not aliens with ray guns. I'm talking about something far more subtle and potentially far more significant: chemistry, complex organic molecules, maybe even the basic building blocks of life itself, hitchhiking across the galaxy on a frozen rock. This is where the conversation gets uncomfortable for some scientists, because we're venturing into territory that's been contaminated by decades of bad science fiction and conspiracy theories. But strip away the nonsense. Look at the hard data. And what remains is a question that's not just legitimate, it's unavoidable. Can life spread between star systems? And if it can, has it already spread to Earth? The theory is called panspermia, from Greek words meaning seeds everywhere, and it's been around since the late 1800s. The idea is simple: life doesn't originate on every planet independently. Instead, it starts in one place and then spreads, carried by comets, asteroids, and other debris that gets ejected into space and eventually lands on other worlds. For most of the 20th century, panspermia was considered fringe science. Respected researchers wouldn't touch it because it sounded too much like the kind of thing you'd hear at a UFO convention. The problems seemed insurmountable. Space is a hostile environment with vacuum, radiation, temperature extremes. Nothing could survive millions of years of interstellar travel. It was physically impossible. Except we kept finding evidence that maybe it wasn't impossible after all. In 1969, a meteorite fell near Murchison, Australia. When scientists analysed it, they found something unexpected: amino acids. Lots of them. More than 70 different amino acids, including several that are critical for life on Earth. And the chemistry proved these amino acids formed in space. Not from terrestrial contamination, amino acids in a meteorite. That was the first crack in the life can't survive in space argument. Then in 2014, the Rosetta spacecraft rendezvoused with Comet 67P/Churyumov-Gerasimenko and deployed the Philae lander. Among the many discoveries, the comet contained glycine, the simplest amino acid, along with phosphorus and other organic compounds. This wasn't contamination. This wasn't wishful thinking. It was direct measurement from a comet that had been frozen in the outer solar system for billions of years. Comets contain the building blocks of life. That's not speculation anymore. It's confirmed fact. Dr. Catherine Altweg from the University of Bern, who led the Rosetta mass spectrometry analysis, put it this way in a 2016 paper: the detection of glycine and other complex organics on 67P demonstrates that comets contain the chemical ingredients necessary for the emergence of life. These molecules were present in the early solar system and were likely delivered to Earth during the heavy bombardment period. The heavy bombardment period, that chaotic first 600 million years of Earth's history, when the planet was getting pummeled by asteroids and comets on a regular basis. We used to think that bombardment was purely destructive, sterilizing the surface with each impact. But what if it was also constructive? What if those impacts were delivering the raw materials needed for life to begin? Now let's connect this to interstellar objects. We know solar system comets contain organic compounds. We know they delivered those compounds to Earth billions of years ago. And we now know that interstellar comets regularly visit our solar system and have been doing so for billions of years. So the question isn't whether interstellar comets can deliver organic material. The question is, what kind of organic material are they carrying? And is it the same as what formed here? Or is it something different? Doctor Fred Hoyle and Dr. Chandra Wickramasinghe, he spent decades arguing that comets could carry not just simple organics, but actual living microorganisms. They pointed to the fact that some bacteria on Earth can form spores that are incredibly resilient, resistant to radiation, extreme temperatures, vacuum, all the things that make space so hostile to life. Most scientists dismissed their ideas as too speculative, but then we started actually testing whether microorganisms could survive in space. In 2007, the European Space Agency conducted an experiment called EXPOS. They took samples of bacteria, lichen, seeds, and other organisms, mounted them on the outside of the International Space Station, and exposed them to the space environment for 18 months. Full vacuum, solar radiation, Temperature swings from minus 157 degrees Celsius to plus 121 degrees C, conditions that should have sterilized everything. When they brought the samples back to Earth, some of the bacteria were still alive, not just dormant alive. Bacillus subtilis spores survived with minimal shielding. Certain lichens actually continued growing. Doctor. Gerda Horneck, who led the study, was cautiously optimistic. These results suggest that certain extremophile organisms could potentially survive transport between planets if protected inside rock or ice matrices. Protected inside rock or ice, like, say, a comet. Then in 2011, researchers published a follow-up study. They took extremophile bacteria and exposed them to simulated interstellar conditions, not just Earth orbit, but the kind of environment you'd experience during millions of years of travel through deep space. High-energy cosmic rays, temperatures near absolute zero, complete isolation. The bacteria survived. Not all of them, maybe only a fraction of a percent. But that's all you need, if even 0.01% of bacteria in a comet survive millions of years of interstellar travel. And if that comet contains trillions of bacteria, then thousands or millions of viable organisms arrive when the comet reaches a new star system. Now, does that mean 3I/Atlas was carrying living bacteria? Almost certainly not. It's a comet, formed in the cold outer reaches of a star system, never in contact with a habitable planet. The likelihood of it containing actual organisms is vanishingly small, but here's what's not vanishingly small: the likelihood that it contained complex organic chemistry. Amino acids, nucleobases, lipid-like molecules, the chemical precursors that, given the right conditions and enough time, can assemble into something alive. Doctor. Jennifer Blank from NASA Ames Research Center has done fascinating work on impact chemistry. She's shown that when comets impact planets, the heat and pressure of the impact can actually create more complex organic molecules from simpler precursors. The impact itself acts like a cosmic chemistry lab, forcing molecules to combine in ways they wouldn't normally. So imagine this scenario: 3I/Atlas, or an object like it, hits early Earth. The impact vaporizes the comet, releasing its organic cargo into the atmosphere and oceans. Some of those organics are destroyed by the heat, but some survive, protected inside larger fragments, and the chemistry triggered by the impact creates new organic compounds from the ones that were already there. Those compounds rain down into the primordial ocean. They accumulate in tidal pools, in undersea thermal vents, in the pockets and crevices of volcanic rock, and over time, millions of years, they start to assemble into more complex structures. Protocells, self-replicating molecules, the earliest, crudest versions of what we call life. Was that chemistry purely terrestrial, formed from ingredients that were already present on Earth? Or was it jump-started by material from another star system, material that had already gone through billions of years of chemical evolution somewhere else? Carried across the void, and deposited here like seeds in a garden we don't know. And here's the frustrating part: we might never know for certain. Because once life starts, once it gets established on a planet, it quickly overwrites the historical record. The earliest life forms consume the organic precursors, metabolize them, incorporate them into their own biology. Within a few million years, there's no pristine organic material left to analyze, no way to trace which molecules came from where. It's like trying to determine which specific wheat grains went into a loaf of bread after the bread has been baked, eaten, and digested. The information is gone, mixed beyond recovery, but we can look at the chemistry. And this is where it gets genuinely interesting. In 2020, researchers analysing data from 2I/Borisov, that second interstellar comet, found something peculiar. The deuterium to hydrogen ratio in its water vapor was higher than typical solar system comets. Deuterium is heavy hydrogen, and its abundance depends on the temperature and pressure conditions when the water ice formed. Higher deuterium suggests colder formation conditions, but it also suggests something else different: chemical processing. Water from Borisov had been through different experiences than water from our own comets. Now, water is water. H2O is H2O everywhere in the universe. But the isotope ratios matter because they tell us about the environment where that water formed and evolved. And if the water is different, what about the organic molecules? What about the complex chemistry that might have been riding along with that water, Doctor? Martin Cordner from NASA Goddard analysed Borisov's composition and noted, "The chemical differences we observe suggest that interstellar comets may deliver material with distinct isotopic and molecular signatures compared to native solar system bodies. This has implications for any prebiotic chemistry they might contribute to planetary surfaces." Distinct signatures, different chemistry, material from environments we've never directly sampled. And if interstellar comets can deliver chemically distinct material to planets, and if billions of these comets have been travelling between star systems for billions of years, then the chemistry of life on Earth, the specific molecules, the specific reactions, the specific pathways that led from simple organics to living cells might have been influenced by material from elsewhere. You might be carrying atoms in your body right now that formed in another star system. Carbon atoms that were once part of an interstellar comet. Nitrogen that condensed in a protoplanetary disk around a red dwarf 50 light-years away. Hydrogen that spent 10 million years drifting through the void before landing here. That's not poetry. That's just statistics. But let's take this one step further into truly unsettling territory. If complex organic chemistry can spread between star systems via interstellar objects, and if life can potentially survive inside protected matrices of rock and ice, then panspermia isn't just a hypothesis about how life started on Earth. It's a potential mechanism for spreading life throughout the entire galaxy. Think about the implications. Life doesn't need to evolve independently on every planet. It only needs to evolve once, anywhere, and then it can spread, carried by comets and asteroids, ejected during planetary formation, during impacts, during close encounters with massive planets. Those objects travel for millions of years, passing through other star systems, occasionally getting captured or crashing into planets. Most of the time, nothing happens. The conditions aren't right. The planet is too hot or too cold, lacks liquid water, has no atmosphere. The organic material arrives but doesn't take root. But occasionally, maybe once every billion times, the conditions are perfect. A young planet with liquid water, an energy source, protection from radiation, and the organic seeds carried by an interstellar visitor find fertile ground. Dr. Edward Belbruno from Princeton has modelled the dynamics of panspermia using galactic orbital mechanics. His calculations suggest that material ejected from Earth could reach other star systems within 5 to 10 million years, fast enough that extremophile bacteria might survive the journey. And if Earth can send material to other stars, those stars can send material here. Which raises a genuinely profound question: is life on Earth unique? Did it start here, independently, using only local ingredients? Or is it part of a galactic biosphere, a web of life that's been spreading between star systems for billions of years, constantly exchanging material, constantly seeding new worlds we don't know? But here's what we do know every time an interstellar object enters our solar system. It's a test of that hypothesis. A data point, a sample from the galactic laboratory. And we're letting them slip through our fingers without adequate study. 3I/Atlas is gone. We took some spectra, some images, but we didn't send a probe to sample its coma. We didn't analyse the organic content of its outgassing. We didn't do any of the detailed chemical analysis that might have answered questions about its prebiotic chemistry. Future visitors, if we're smart, will be ready. We'll have spacecraft on standby, ready to intercept and sample the next interstellar comet that comes through. We'll analyse its isotopes, its organic molecules, its chemical complexity. Because here's the thing, we're not just studying rocks and ice. We're potentially studying the mechanism by which life, or at least its chemical precursors, spreads across the galaxy. We're investigating whether biology is a local phenomenon or a cosmic one. And if it turns out that life is cosmic, if we find evidence that Earth's biology was seeded or influenced by material from other star systems, then everything changes. Our origin story changes. Our place in the universe changes. The question of whether we're alone changes from "are there aliens" to "how interconnected is the web of life we're already part of?" Dr. David Grinspoon, an astrobiologist who's written extensively about panspermia, put it beautifully: if life can spread between worlds, between star systems, then in a very real sense we're not separate from the rest of the galaxy. We're family. Distant cousins, perhaps, but related through a shared ancestry that stretches across light years and billions of years. Family, related, part of something larger, or maybe not. Maybe life on Earth is completely independent. Maybe the chemistry that led to the first cell was purely terrestrial, untouched by foreign influence. But we'll never know unless we look, unless we study these interstellar visitors with the seriousness they deserve, unless we stop thinking of them as mere curiosities and start treating them as potential bridges between worlds. Because that's what they are. Bridges, connections, silent couriers carrying messages we're only beginning to learn how to read. And 3I/Atlas, that small, active comet from an unknown star system, might have been carrying a message we'll never decode. A sample of chemistry from another corner of the galaxy, forever lost because we weren't paying close enough attention. The question isn't whether life can travel between stars. The question is, has it already arrived? And are we looking closely enough to notice? The future is coming faster than you think, and it's going to force us to confront questions we're not ready to answer. Remember when I mentioned the Vera Rubin Observatory? That beast of a telescope in Chile that's going to revolutionize how we detect interstellar objects. Well, is not just going to find more visitors, it's going to find so many that our entire relationship with the cosmos is about to change. Let me paint you a picture of what the next decade looks like. It's 2027. You're scrolling through your newsfeed over morning coffee, and there it is, buried between celebrity gossip and political drama. Astronomers detect 5th interstellar object this month. 5th. This month. And you barely register it because it's become routine, expected, almost boring. The headline doesn't mention that this particular object is unusual, darker than others, moving faster. Possibly the fragment of a planet that was destroyed in a catastrophic collision billions of years ago. That context is buried in the article that maybe 0.1% of people will actually read. But the scientists, they're not bored. They're overwhelmed. Dr. Matthew Holman, speaking at a 2024 conference about Vera Rubin's capabilities, said something that should make you sit up and pay attention. We're about to go from a sample size of 3 to a sample size of hundreds or thousands, and we don't have the infrastructure, human or computational, to properly study them all. Think about what that means. Right now, when we detect an interstellar object, it's a major event. Observatories worldwide coordinate. Papers get published. Graduate students write dissertations. Every piece of data is precious. But when you're detecting 1 or 2 per week, you can't give each one that level of attention. You have to prioritise, make choices, and that means some visitors, maybe most visitors, will get logged, catalogued, and essentially ignored. It's like being handed a library containing books from civilizations across the galaxy. But you'd only have time to read the titles. Maybe skim a few chapters if you're lucky. The information is there, available, but the resource limitations mean most of it will never be fully examined. And here's where it gets really interesting and really scary, because as our detection rate increases, so does our awareness of how many near misses we're having. In 2026, there's going to be an object. I can't tell you its designation because it hasn't been discovered yet, but statistically, it's almost certain to happen. An interstellar visitor that passes within lunar distance that's closer than the Moon orbits Earth. Not a collision, but close enough that it'll be visible to amateur astronomers. Close enough that people will be able to see it moving across the sky with binoculars. When that happens, not if, when the public reaction is going to be complicated. Some people will think it's amazing, a once-in-a-lifetime celestial event. They'll host viewing parties, post photos on social media, make TikToks about the cosmic visitor. Others will panic and roar. Because for the first time, the abstract threat of interstellar objects will become viscerally real. If this one passed so close, what about the next one? What if the next one doesn't miss? And the scientists will have to answer uncomfortable questions. How much warning did we have? Could we have deflected it if it were on a collision course? What's our plan for next time? Dr. Amy Mainzer, principal investigator of the NEO Surveyor mission, addressed this scenario in a 2023 NASA briefing. Increased detection capability is a double-edged sword. Yes, we'll have better awareness, but we'll also have to manage public perception of risks that were always there but are now visible. Visible. That's the key word. The risks aren't new. They've been there all along. We're just finally developing the ability to see them. But let's zoom out even further. Because the near-term future, the next decade of increased detections, is just the beginning. The real revolution happens when we start finding patterns. Right now, each interstellar object is a standalone mystery. 1I/Oumuamua, 2I/Borisov, 3I/Atlas. We study them individually, trying to extract whatever information we can before they vanish. But we can't see the forest for the trees. Once we have hundreds or thousands of detections, that changes. Suddenly we can do statistics. We can look for correlations, trends, anomalies. We can start asking bigger questions, like are there streams, clusters of interstellar objects that share similar trajectories and compositions, suggesting they came from the same source system or the same ejection event. Dr. Fabo Feng from the University of Hertfordshire has proposed exactly this type of analysis. In a 2022 paper, he suggested that if a massive planetary disruption occurred in a nearby star system within the last 10 million years, we should be able to detect its signature in the interstellar object population passing through our solar system. It would be like finding multiple pieces of the same shattered vase scattered across a room. Dr. Feng explained. Each piece individually tells you little, but together they reveal the shape of what was broken. Imagine if we found that. Imagine if we detected 20 or 30 interstellar objects over the course of a few years, all with similar compositions, similar trajectories when traced backward, all pointing to a common origin point in space. That would tell us something profound. We'd be witnessing the aftermath of planetary system destruction. A world or worlds that were torn apart, possibly millions of years ago, and the debris is still washing up on our shores like wreckage from a distant shipwreck. And here's the creepy part: if we can identify the source system, if we can point our most powerful telescopes at that star and look for any surviving planets, we might see a system that's been fundamentally altered. Maybe a gas giant in a highly eccentric orbit, evidence of a close stellar flyby. Maybe an asteroid belt far more massive than it should be. Maybe nothing at all, a star stripped bare of planets, with only scattered debris to hint at what once existed. We would be cosmic forensics investigators, studying crime scenes that occurred before humans existed, but the patterns might reveal something even stranger. What if we discover that interstellar objects aren't randomly distributed? What if there are streams in galactic space regions where interstellar objects are more common because they're following similar paths through the galaxy? Our solar system is moving through space at 500,000 miles per hour. We're not stationary. We're orbiting the galactic centre along with billions of other stars, each with its own velocity vector, and just like schools of fish create patterns in the ocean, the collective motion of star systems might create patterns in the distribution of interstellar debris. If those patterns exist, we could use them predictively. We could calculate when Earth is moving through a dense region of the interstellar stream and expect more visitors during those periods. We could identify low-risk zones and high-risk zones. Dr. Corinne Baylor-Jones from the Max Planck Institute for Astronomy has been working on exactly this kind of galactic cartography. His team is building models of stellar kinematics, how stars move through the galaxy, and correlating that with the trajectories of known interstellar objects. If the models are correct, he said in a 2024 interview, we should be able to predict periods of increased interstellar object flux based on our position in the galaxy. It's not precise, we're talking about trends over millions of years, but it would give us a statistical forecast. A forecast, like weather prediction. But for interstellar visitors, high chance of cosmic debris this epoch, pack an umbrella, or, build better telescopes. But here's where the future gets really wild: what happens when we find something that doesn't fit the pattern. Because in any large dataset, there are outliers, objects that move wrong, look wrong, behave wrong. And when you're sampling visitors from across the galaxy, eventually you're going to encounter something genuinely anomalous. Maybe it's an object with impossible chemistry isotope ratios that don't match any stellar formation model. Maybe it's an object that's too pristine, showing no signs of space weathering despite clearly being millions of years old. Maybe it's an object that accelerates in ways that can't be explained by outgassing or radiation pressure. Oumuamua, you might recall, was exactly this kind of outlier. Its acceleration as it left the solar system couldn't be fully explained by standard cometary outgassing. Most scientists think there's a natural explanation, maybe hydrogen ice sublimating, maybe some exotic process we haven't considered. But that tiny percentage of uncertainty, that's what allowed speculation to flourish. Now multiply that by hundreds of detections. Statistically, some of them will be weird. Not alien artifacts, let's be clear, but genuinely puzzling objects that challenge our understanding of planetary formation, stellar evolution, or interstellar space. And the public discourse around those objects is going to be intense. Because once you normalize the idea that visitors from other star systems regularly pass through, once that becomes part of the cultural background, people start asking the next logical question: could any of them be artificial, Doctor? Avi Loeb, yes. Him again has been pushing this question hard. His Galileo project, launched in 2021, is specifically designed to search for evidence of extraterrestrial technology. And while most scientists think he's wildly optimistic at best, he's not wrong about the underlying logic if technological civilizations exist elsewhere in the galaxy. And if they've been around for millions or billions of years, then statistically some of the interstellar objects we detect might be their artifacts, probes, defunct spacecraft, autonomous explorers, maybe even debris from conflicts or accidents we can't imagine. The probability is low, vanishingly low, but it's not zero. And when you're detecting hundreds of interstellar objects, even a low probability event starts to become plausible. I'm not saying we're going to find alien spacecraft. I'm saying that as our sample size increases, the question stops being dismissible. It becomes something we actually need to check for, even if only to rule it out. And that means developing criteria. What would artificial actually look like? How would we distinguish it from natural but unusual? What observations would be sufficient to make that determination? These aren't rhetorical questions anymore. They're active research topics. Scientists are literally writing papers about detection strategies for interstellar artifacts, just in case Dr. Jacob Hack Misra from the Blue Marble Space Institute has proposed spectroscopic signatures that might indicate technological materials-specific chemical compounds or isotope ratios that don't occur naturally. Dr. Ravi Kopparapu from NASA Goddard has suggested geometric analysis looking for shapes and surface features that imply design rather than geological processes. Will we find anything? Almost certainly not. The galaxy is big. Civilizations are probably rare if they exist at all, and the odds of one of their artifacts happening to pass through our solar system at precisely the moment we're technologically advanced enough to notice astronomical. But, and this is important, we're going to look anyway, because the cost of checking is low, and the implications of finding something would be literally world-changing. And that's the future we're walking into. A future where interstellar visitors are common enough to be routine but rare enough to be exciting. Where each detection might reveal new science or might just be another data point. Where we're constantly balancing between the wonder of discovery and the anxiety of what might be discovered. It's going to change how we see ourselves, how we see Earth, how we see our place in the galaxy. Because right now, in 2025, most people still think of Earth as separate, protected, our own little bubble in space. Sure, we know intellectually that we're part of the galaxy, but it doesn't feel that way. It feels like we're here and everything else is out there. But when you're tracking interstellar objects weekly, when you've catalogued hundreds of visitors from across the galaxy, when you've studied their chemistry and traced their origins, and realized that material from distant star systems is literally raining down on Earth every single day that separation dissolves, we stop being inhabitants of Earth and start being inhabitants of the galaxy. We stop thinking about our planet as a closed system and start recognizing it as a node in a vast network of matter and energy exchange. Dr. Sarah Seeger from MIT, who's dedicated her career to studying exoplanets and the search for life, said something profound in a 2023 lecture. The discovery of interstellar objects is forcing us to adopt a galactic perspective. We're not just Earthlings anymore. We're galactic citizens, whether we're ready for that identity or not. Galactic citizens, that's what we're becoming. Not through space travel, we're nowhere near that, but through awareness, through understanding, through the realization that our cosmic neighborhood is far more interconnected than we imagined. And 3I/Atlas, that relatively small, relatively unremarkable comet that passed through in 2019, was part of that awakening. It was a messenger telling us that the future's already here. We just need to pay attention, because the encounters are going to keep coming. More objects, more data, more questions, and eventually, maybe sooner than we think, we're going to detect something that changes everything. Something that forces us to completely revise our understanding of planetary systems, or galactic evolution, or the distribution of life What will that object be? When will it arrive? What will it teach us? Those are questions we can't answer yet, but they're coming. The math guarantees it, the statistics demand it, and the exponential increase in detection capability ensures it. The only question is, will we be watching when it happens? Or will it slip past unnoticed, like so many others before it? Another missed opportunity to understand the universe we're part of. So let's pull back, way back. Let's look at the big picture that makes 3I/Atlas and every other interstellar visitor so deeply, fundamentally terrifying. It's not about the collision risk, though that's real. It's not about the alien chemistry, though that's fascinating. It's not even about the detection challenges, though those are significant. It's about what these objects force us to confront the reality of our cosmic situation. And that reality is far stranger and more unsettling than most people realize. Here's the truth that 3I/Atlas reveal the solar system is not your home. Not in the way you think. You probably imagine the solar system as a discrete thing. A family, the sun and its planets, the asteroids and comets, all of it born together for 6 billion years ago from the same molecular cloud, all of it related, all of it ours. Everything inside some invisible boundary line is the solar system, and everything outside is interstellar space. Two separate domains. That mental model is completely wrong. The solar system isn't a closed system. It never was. There is no boundary, no fence, no protective bubble keeping the rest of the galaxy out. We're not separate from the interstellar medium. We are part of it, swimming in it, constantly exchanging material with it. Every single day, tons of interstellar dust drift into the solar system. Not from comets or asteroids, just ambient dust grains that happen to be passing through this region of the galaxy. They rain down on Earth's atmosphere, burning up as microscopic meteors that you never notice. You've probably inhaled atoms that spent millions of years drifting between the stars before ending up in your lungs. Every single year. Larger objects, pebbles, rocks, maybe even small asteroids pass through without being detected. They come from other star systems, cruise through our neighborhood for a few weeks or months, and leave, anonymous visitors that we'll never catalogue, never study, never even know existed. And every few years something big enough and bright enough gets detected. Oumuamua, Borisov, 3I/Atlas. We spot these ones purely by luck. Right place, right time, right brightness. We study them, learn from them, and watch them disappear back into the void. But here's what should keep you awake for every one we detect. There are hundreds we don't. For every 100 we might eventually detect with better technology. There are thousands that will remain invisible. And for every 1,000 interstellar objects in our immediate neighborhood, there are billions beyond our detection range, scattered throughout the galaxy. The Milky Way contains somewhere between 200 and 400 billion stars. Each one probably ejected billions of objects during its planetary formation phase. Do the math actually? Don't, because the numbers are incomprehensible. But the point is, the space between stars is absolutely packed with debris, wanderers, exiles, the cast-off remnants of planetary systems across the entire galaxy. And all of it is in motion. All of it is travelling. All of it is going somewhere, even if that somewhere takes millions of years to reach. Dr. Amaya Morrow-Martin, whose work we've discussed before, put it this way in a 2021 paper: the galaxy is not a collection of isolated star systems. It's a single, interconnected system where material constantly flows between stellar neighborhoods. On timescales of billions of years, every star system has likely exchanged material with thousands of others. Every star system has exchanged material with thousands of others. Read that again, let it sink in. The atoms in your body didn't all originate in our solar system. Some of them, maybe many of them, came from elsewhere. From star systems dozens or hundreds of light years away. From environments you can't even imagine. from worlds that might have existed and died before our sun was born. You're not just made of stardust, you are made of galactic dust. You're an assembly of materials that have been mixing and travelling and exchanging between star systems for billions of years. That's the cosmic perspective that 3i/Atlas forces us to adopt. And it's profoundly disorienting. Because if Earth is not a closed system, if we're constantly receiving material from elsewhere and sending material outward, then where do we draw the line? What makes something terrestrial versus alien? What makes Earth ours? The answer is, there is no line. There is no clear division. We are part of a continuum that stretches across the entire galaxy. And if material flows freely between star systems, what else flows? Information chemistry, complexity, life itself. That's the question that panspermia raises, but it's bigger than just asking whether microbes can survive interstellar travel. It's asking whether biology life as a phenomenon is local or galactic. Think about it this way: if life can start on one planet and spread to others via interstellar objects, then the galaxy doesn't contain billions of separate, independent origins of life. It contains a much smaller number of original Genesis events, each one spawning a vast lineage that spreads across light years and billions of years. Maybe life only originated once in this entire region of the galaxy. One planet, one primordial soup, one lucky combination of chemistry and energy and time, and from there it spread, carried by impacts, by comets, by the slow, random walk of interstellar debris. Earth might not be the origin point. We might be a branch on a family tree that extends across dozens or hundreds of star systems, related to organisms on planets we'll never see, descended from ancestors that arose on a world whose star burned out 1 billion years ago. Or maybe life originated here. Maybe Earth is the source, and right now, this very moment, some fragment of terrestrial biology is travelling through interstellar space, locked in ice, dormant but viable, heading towards some distant star system where it'll arrive long after human civilization has risen and fallen. We might be the ancestors of alien life, future organisms on distant worlds. If they ever develop science and trace their biochemistry backward, might discover that their origin point isn't their own planet, it's Earth. They might realise they're descended from something that hitched a ride on an interstellar rock billions of years ago. How's that for a mind-bending reversal of perspective, Doctor? Chandra Wickramasinghe, one of the original proponents of panspermia, said in a 2019 interview, if panspermia is real, then the question of where is life becomes meaningless. Life isn't confined to specific planets. It's a galactic phenomenon, constantly spreading, constantly evolving, using the entire galaxy as its substrate. The entire galaxy as its substrate? That's not a metaphor. That's potentially the literal truth. And if it's true, then the implications are staggering. It means astrobiology isn't just about finding life on Mars or Europa or Enceladus. It's about understanding how life propagates across galactic distances, how it survives the void, how it adapts to new environments, how it might have arrived here in the first place. It means that when we search for biosignatures on exoplanets' atmospheric oxygen, methane, chlorophyll signatures, we might be looking at our own distant relatives, life that shares a common ancestor with everything on Earth, even though it's separated from us by hundreds of light years. It means the tree of life isn't rooted on Earth. It's rooted in the galaxy. And we're just one branch among countless others, most of which we'll never discover. But let's bring this back down to something more concrete. Because the cosmic perspective isn't just philosophically interesting, it has practical implications for how we think about planetary defense, resource utilization, and our future in space. If interstellar objects are common, if they're constantly flowing through the solar system, then they're not just threats, they're opportunities. Think about it, every interstellar visitor is a free sample of another star system's materials. We don't have to travel light years to study what's out there, it comes to us. If we can intercept these objects, study them, maybe even capture them, we gain access to resources and information that would otherwise be completely beyond our reach. Doctor. Andreas Hein from the Initiative for Interstellar Studies has proposed exactly this. He calls it interstellar mining, using robotic spacecraft to rendezvous with interstellar objects, extract samples or even bulk materials, and return them to Earth or utilize them in space. These objects are already in our neighborhood. Doctor, Hein explained in a 2023 paper. The delta Vi required to intercept them is often comparable to reaching near-Earth asteroids, and the scientific and economic value could be enormous. Imagine that. We could be mining materials from other star systems without ever leaving our own solar system. We could be analysing geological samples from worlds we'll never visit. We could be extracting water, metals, organic compounds resources that are identical to what we'd find in our own solar system but carry the added value of being from elsewhere. And if we develop that capability, if we build infrastructure for intercepting and studying interstellar visitors, we'd also be building infrastructure for planetary defense. The same spacecraft that can rendezvous with a comet for scientific study can potentially deflect one that's on a dangerous trajectory. But there's a darker implication too. If we're receiving constant input from the rest of the galaxy, if material from elsewhere is always arriving, then Earth's environment isn't purely a product of terrestrial evolution. It's been contaminated. If you want to use that word, by external factors for billions of years. Every major impact event in Earth's history didn't just crater the surface and kill organisms. It also delivered foreign material, chemistry from elsewhere, isotopes with different ratios, organic molecules with slightly different structures. And if some of those impacts were from interstellar objects rather than native solar system asteroids, then the influence goes even deeper. We might have atmospheric gases that originally came from comets formed around other stars. We might have ocean water with isotope signatures that reflect mixing between terrestrial and interstellar sources. Earth's chemistry, the very composition of the planet you're standing on, is a blend, a mixture, a cosmic smoothie made from ingredients local and foreign, all mixed together over billions of years until you can't separate them anymore. Dr. Lindy Elkins Tanton from Arizona State University, who studies planetary formation and evolution, addressed this in a 2022 lecture. We tend to think of Earth as having a single, coherent composition derived from the solar nebula, but the reality is more complex. Earth has been accreting material throughout its entire history, and some of that material definitely came from beyond the solar system. We're only beginning to understand what that means for our planet's chemistry and evolution. What that means is you can't point to any specific thing and definitively say, this is purely terrestrial. The boundaries are too blurry. The mixing is too thorough. We are galactic composite entities living on a galactic composite planet. And once you fully internalize that perspective, once you really understand it at a gut level, the entire concept of alien starts to break down. Because what makes something alien, origin from outside our solar system? Well, by that definition, a significant fraction of Earth is alien, composition that's different from terrestrial materials. Except our definitions of terrestrial are based on limited sampling and might not account for the full range of variation. The line between us and them, between here and there, is far less clear than we'd like to think. And that's terrifying. Not because it's dangerous, though it might be, but because it undermines our sense of place, our sense of belonging, our comforting illusion that Earth is a discrete, knowable, bounded system. It's not. It never was. We just didn't have the technology to see the truth until recently. 3I/Atlas didn't change anything. The reality was always there, but its detection, its study, the way it forced astronomers to confront the commonality of interstellar visitors that changed our awareness, that cracked open the comfortable illusion and let the cosmic truth seep in. We are not separate from the galaxy. We are embedded in it. We are products of it. We are, in a very real and literal sense, galactic organisms inhabiting a galactic world that's part of a galactic ecosystem we're only beginning to comprehend. And the thing is, we can't unknow this. We can't go back to imagining Earth as an isolated oasis in an empty void. We've seen too much, detected too much, understood too much. The future will bring more detections, more data, more understanding. And with each discovery, the cosmic perspective will deepen. The interconnections will become more apparent. The realization of how thoroughly we're woven into the galactic tapestry will become inescapable. Some people will find this liberating. We're part of something vast, ancient, and beautiful. We're connected to processes that span light years and billions of years. We're galactic citizens, and that's amazing. Others will find it existentially disturbing. Our planet isn't special. Our origins aren't unique. We're just one more accidental assemblage of cosmic debris that happened to develop complexity and consciousness. Nothing more. Both reactions are valid. Both are probably true simultaneously. But here's what I think is the most important takeaway 3I/Atlas and its fellow interstellar visitors are forcing humanity to grow up, to abandon childish notions of cosmic isolation and embrace a more mature, more complex, more accurate understanding of our place in the universe. We're not alone on a special planet in an empty cosmos. We're part of an ancient, interconnected galactic system that we're only beginning to map and understand. And yes, that's terrifying, because growth is always uncomfortable. Because seeing the full picture means confronting how small we are, how recent we are, how contingent our existence is on processes that dwarf us in scale and time. But it's also the most profound thing humanity has ever discovered. It's the answer to questions philosophers have been asking for millennia. What is our place in the cosmos? Are we separate or connected? Are we alone or part of something larger? The answer, delivered by silent wanderers like 3I/Atlas, is we are connected. We are part of something larger. We always have been. We just didn't know it yet. And now that we know, now that we've seen the evidence with our own telescopes and calculated the trajectories with our own computers, we can never go back to not knowing. The big picture is terrifying, not because it threatens us, though it might, but because it reveals us. It shows us what we really are, temporary patterns of organized complexity on a planet that's more galactic than terrestrial, in a solar system that's more permeable than isolated, in a galaxy that's more interconnected than we ever imagined. That's what happens when you look at the big picture. That's what 3I/Atlas, a small comet from an unknown star, briefly passing through on its way to forever, taught us. We are part of the galaxy. The galaxy is part of us. And the distinction between the two was always an illusion. Welcome to the cosmic perspective. It's beautiful and terrible and absolutely undeniably real. And somewhere out there, right now, another visitor is on its way. Maybe it'll arrive tomorrow. Maybe in 100 years. Maybe in 1,000. But it's coming. They're always coming. They always have been. The question is, what will the next one teach us? What truth will it reveal that we're not ready to hear? What will we discover when we finally look closely enough, because the universe isn't done with its lessons? It's only just begun showing us how much we don't know. And honestly, that might be the most terrifying thing of all. The silence of space continues. The visitors keep coming, and we keep watching, learning, slowly understanding that the story we thought we knew about our planet, our solar system. Our place in the galaxy was just the prologue. The real story is only beginning.